slide or anything, I can.
Okay, yeah, great. You might
Okay.
as well share the slides.
Yeah. So let me go and pull up the.
So yeah, it was an interesting talk on
Oh, thanks. Were you
quantum.
able to
Oh,
look? Were you able to do the whole thing? I mean, it's
yeah,
like hour and a half. It's little more than usually I do because I put some, things that will help. Hopefully, it'll help people. You can see it now, right?
yeah, yeah, we can see that.
Okay.
Okay, so
So,
I mean, if you want to go bigger screen on
oh,
the
I have to be on that screen, I think. I have to be there. Anyway, I will.
okay, so
Yeah.
there was a few things that I was curious about. So it was mainly a talk on quantum gravity, but it had a lot of how would you say, sort of diversions into different like string theory, M theory.
Yeah.
So it was good. It was quite comprehensive, I suppose.
Oh, thank you.
You didn't, as you mentioned, you didn't go into any of the kind of mathematics behind it.
Yeah.
But
Yeah.
I think that's a good idea because that
Uh-huh.
could tend to distract from things a bit, especially when you
Yes.
just want to get the points across. But and the maths can be kind of difficult and a little bit off-putting as well sometimes. So,
Yeah.
but it is something that we'll have to look into a bit more. So I thought maybe I'd direct the questions more in that area. It doesn't
Okay.
have to be like equations per se, but just the concepts behind some of the concepts that you brought up, if you will.
Okay.
So I don't know which slide it is, but
Should I play the slide or you want me to
yeah, you
show
might
a
as well. Yeah,
slideshow?
make it make it larger. There was one right, so it's probably early on in the slideshow. There's you mentioned string theory is a top-down approach, whereas other
Ah,
I think by
oh,
Gell-Mann
excellent.
and others were
Ah,
bottom up, was it? And string theory was top
yeah,
down. Sorry. Yeah, yeah.
yeah, and then yeah, the emergent. I mean the Steven Weinberg. So I will go to the slide. Let me.
Oh, yeah, it was Weinberg. Sorry, not Gell-Mann.
Yeah. So let
Okay,
me.
so yeah, you need to
Let me
make that
see.
bigger though. We can kind of see you're in the notes screen.
Yeah, that's the one that's showing up. So I'm going there. Let me
Okay.
see how I get there. Because sometimes this cursor doesn't go over there. Oh yeah, now it's there. So I have to hide present review. Oh, sorry.
There we go.
Oh, now it's working. I think.
Yeah, it's looking fine.
Just the subtitles, maybe I pull it out.
Stop.
Okay. So now I think we are okay. So let
So
me
earlier in the slideshow, I think. Yeah. Or maybe it's the first slide, is it? Yeah, it is. String
this is
theory
one.
and the top-down approach. So what is meant by that? I think I've heard of this before, but I've forgotten what it pertains to.
Okay. So string theory. Okay. So the EFT is bottom up. So this is I think I let me Steven Weinberg. Yeah, Steven Weinberg is the one that bottom up approach general relativity. So the string theory is top down in the sense that it starts with the quantum aspect, right? The quantum aspect. Uh, so it starts with the idea that instead of the particles, you have strings, the vibrating strings. So it is already going to the next level. I mean, the whole thing about quantum mechanics or the quantum physics is about the particle and the field, right? They're they're kind of together. Whereas the next level, the string theory goes to the next level that it is vibrating strings and based on the time aspect, right? So it is going, upwards in terms of the hierarchy. So you have classical physics, then you have quantum mechanics, you have general relativity and quantum mechanics, maybe parallel, and above that is your, you know, is this string theory. So string theory talks about already quaternions. It's already accepted quaternions, not only quaternions, but also dimensions of higher dimensions vibrating. So it is much, much higher level. So that's the idea. So it starts down and then try to come to the gravity. Gravity is much lower. Like when I do, the way I understand it is when I did my rank tensor, so I can see it from a different angle. You see, so I have ranked the time as a rank 6 tensor. Then I have to grade it down because when you come to the Schwarzschild matrix, things like that, it is rank 2. So the real things are way down. You have to grade down to all the way to vector rank 1. So string theory doesn't go in that direction, but I can see how the string theory is going. So the string theory goes up with the higher dimensions, with the quaternions and all those things, the vibrations, the vibrational modes. So it is much higher in terms of hierarchy of the theory. And then but for gravity, it has to come down. It has to come down all the way to general relativity. So it thinks general relativity and quantum mechanics are subsets of string theory. And then it starts next level, but it actually what you call automatically takes into account the quantum mechanics. But for general relativity, it has to come down and then look at the gravity from a different point, from point of the strings vibrating, how that connects to general relativity, to gravity. That's a very difficult thing. So that's what Swampland conjectures. For example, Swampland conjecture is the important thing. He says there is no global symmetry, right? Swampland. So gravity essentially is a local phenomena, that everybody kind of understood that, and in general relativity also, they have to come to localized aspect. So then the question, the quantum mechanics raises the question: is it non-locality or locality? So that's why the next one I want to do Bell's theory. I want to do M theory, but I found that in between that I had to do the Bell's inequality. That becomes important. The non-locality versus the locality aspect. So how does the gravity come into picture? So top-down approach is that you can look at the global picture, the string theory. It looks at that, and then when you see come to the local thing, which is top down, then you get to the gravity. So the gravity is a subset of that. You come down in the strings, and then the local things, something happens, this formula, then it becomes understand gravity. Whereas the EFD, which is the emergent field theory, says that it starts from your classical things, but mostly standard model, and the beginning, idea is general relativity. So it builds up the general relativity, and then from general relativity goes up to the quantum mechanics. So if you see that it's not a straightforward up and down, I think it will be wrong to consider it straightforward, but it's like a curved up and down, So
well, yeah, but you could say that they're also unifying it from quantum mechanics to general relativity.
Yeah. So that's the way you can look at it. In a rough way, you can say, okay, string theory looks at from quantum mechanics to general relativity, whereas the Steenberg's EFT, things like that, looks up from general relativity to quantum mechanics.
Okay, that's a very simple, straightforward answer. Yeah, I like that.
Yeah.
It also reminded me a bit of, I listened to a very good talk, the details of which I don't remember, but the general idea was, how with so-called Feynman diagrams, where
Uh-huh.
you have all of these different tree level. Well, you have tree level, and then you have the higher versions where there's like loops
Ah.
and branches. So and string theory does something a little bit different. Instead of because it takes like the aggregation, the sum over of all the particles on the topologies. So
Uh-huh.
you'd have like I guess a torus would be one topology, and you might have a torus with two holes in it, so genus 2, genus 3 maybe. But so the idea is that you're summing over topologies instead of
Okay.
all of these tree diagrams, and so that's like a different kind of direction, I suppose. Like you could think of it that way, but they were just pointing out that at the end of the day, it's the same problem, because with the Feynman diagrams, you have to sum over all of these different diagrams to get a kind of as a perturbative, where they get closer and closer to an answer that's correct, but never actually get there because it's an infinite series. And the same problem then with string theory occurs, because you sum over all these topologies, but you can never actually get to the bottom, and they were never able to discover exactly which topology was the one that can be associated properly with string theory. I think they found like over 10,000 of these Calabi-Yau manifolds, so they could never decide which one is exactly the correct one. Also, I believe that a lot of string theorists even don't fully understand the Calabi-Yau manifold. Is it? Yeah, the guy who came up with this. It sounds like two people came up with it, but I think it was just. But I did hear Lee Smolin say that no one understood what he was talking about. I don't know if that's true. But anyway, thanks for that answer. That was very.
Yeah.
I thought that was useful. I don't know if you want to say anything on that. What I said, if that's does that.
Yeah, it's so interesting. What you said is, I think, sums up the sense. Yeah, what you say sums up the whole thing. I had to watch it again. I think you have put a lot of things together about generative, about how all different physicists see it, and especially Lee Smolin. I think he comes from the measurement aspect, and also one specific thing. What is he is concentrating on now? So I'm not sure, but
Lee is.
I do agree partly. Some of things he was.
I think he's a loop.
Yeah, loop. Yeah.
So
now
that's been in the news a lot recently.
Gravity.
In the physics news, from the perspective of, I think there was a result from a Chinese research paper which showed that one of the predictions that Lee made didn't come to pass or something like that. But so people were saying, oh, this means that string theory wins because loop quantum gravity's prediction failed.
Your audio is.
Already? I think both of our audios are kind of going.
Yeah.
So did you hear? Did you hear what I asked or what I'm saying?
You are not able to hear.
Yeah, you.
Now I'm hearing. Now are you?
Okay.
Now I'm okay.
Good. Okay, yeah, you were breaking up a bit, but we're fine now, I think. So let's see. I think just
the internet
there about. Huh? Well, you know what I'll do? I'll try and switch off my camera. That might help. Okay. Can you hear me? Can you hear me now? Hello? Oh. I'd have to leave and come back.
Yeah, it is on. It is.
I'm gonna. Hello? Can you hear? You can hear me, yeah. What you could do, Rajan.
Yeah, now it's better. Yeah.
Good. You seem to have two feeds coming into the. You see at the bottom there. There's you, and then there's you again.
Oh yeah.
Maybe remove that one.
I forgot to mute the other one. It's just to. So I had to mute the other one.
Oh, that's probably, maybe that's where
Now
the
it's better,
interference is
right?
coming from. Okay, great. Yeah, because we could be
Hello?
talking over each other and the
Yeah, I
sound.
forgot. Normally, I use the other one.
Okay, but yeah, if you want to remove it, if
Is
the
it okay
problem
now? Yeah.
persists, you can remove it. Okay, so the other issue then, oh yeah, so loop quantum
Yeah.
gravity, and yeah, but apparently I was listening to an interview with Carlo Rovelli there. I didn't actually finish it, but he said that it's not an issue because they'd already discounted it theoretically. I don't know if that doesn't necessarily mean that loop quantum gravity is correct, but it's not a defeater on their part. I don't think they think. So yeah, and then I think Lee Smolin has some health problems as well. So his research is now kind of focused into how to mitigate or find a cure for Parkinson's. So that's a big side thing that he's doing. So I wish him well on that, because it's Parkinson's is
he like in the 80s?
What?
Oh yeah, it's yeah.
Oh, it's terrible. Like, it's a really bad disease. So
is he in the 80s? In his 80s or?
Is he that old? I mean, he could be, yeah. But
like Hawking, what did he have? Did he have?
Oh, I can't remember what Hawking had. No, sorry. No, it's not coming back to me. Sorry. But okay, well, we'll move on anyway with the general questions, because I think
sure. No problem.
Your presentation raised a lot of interesting points. So we have this notion that you bring up often is global and gauge symmetries. So in one slide, there was an error that you picked up in your presentation. I can't remember what it was. Says could unite the could unite the strong, weak, and something as global EM for electromagnetic forces. So I'm not sure what slide that is, but there's an error. It says could unite the weak, strong, weak as global electromagnetic forces. So I assume you were trying to say could unite those strong, weak, and electromagnetic forces as global EM forces. Yeah, or where is it? I don't think it's that slide. Or that one.
This is the Higgs mechanism.
There it is. It is Planck limits and beyond. A more fundamental theory, possibly a gut, could unite the strong, weak as global.
Oh, this one you mean? Yes, unite the strong, weak. Oh, this it's a spelling mistake I had. As weak.
Yes. So I assume you mentioned
right. I had an extra. I should correct.
And electromagnetic forces, was it?
Well,
as global.
Yeah.
Well, what's the correction there?
I think I should remove that one. So it should be unite the strong, probably and the weak. I should correct it as strong and the weak as global electromagnetic forces, something like that. I think
that makes sense. Yeah. Okay. So yes. So we have the mention of global there. Later on, I think you mentioned Lagrangian is unchanged by certain local transformations. And then you mentioned higher form symmetries.
Yeah.
So I'm just interested because then this all links to the covariant, isn't it? In general relativity, Lorentz groups, it's covariance. So, but you know, all this language, I come across it, but not too often. But more recently, I've been coming across this distinction between global and gauge symmetries, and I'm just really trying to understand it. So we might spend the rest of the time trying to nail that down. So a global symmetry obviously is, I mean, there's loads of global symmetries, aren't there? There's conservation laws. If we do an experiment on a table in Japan, and then we do it in Ireland, we expect the same results, even though they're translated in space.
Yes.
You know, things like that, or time. different time periods that we should get the same answers. So these are different kind of global symmetries, and then we have gauge symmetries, which don't follow those rules or something. They're local events can, you know, or they are kind of local, or they're not even really real or something. But so when you're talking about global EM forces, okay, maybe you could talk a bit about that, but and why like Lagrangian would be unchanged by certain local transformations. Now, I think you mentioned something about local and non-local earlier, to do with who was it again? Bell's inequality. But I don't, when it's saying local here, local transformations or local symmetries as opposed to global, does it, I mean, yeah, local and non-local could probably tie into that, but in general, when we're just talking about it on a, maybe in a general sense, we don't need to discuss, like, the difference would be local and global, wouldn't it? Rather than local and non-local.
Yeah, eventually. See, what I'm following is how people understood in terms of history. I'm not judging or analyzing. That we can do, you know. This will help the stage develop, and it kind of confuse things. So I'm trying to bring out that aspect, but we have to sort it out, like you said, between global and local symmetries, you know. So subsequently we will, as the episodes progress from beyond 8 is mostly Bell's. Yeah, the Bell's thing come in the picture there, non-locality and locality thing. The 8th episode will have a few slides on that. So after that,
I think
then a 9th and a 10th, we will be designing such a
that's probably a bit that kind of higher level stuff. But because you brought up these concepts of global and gauge symmetries at this point, I think we should be clear what
something's happened.
Oh, well, if you try and remove that video I said at the bottom.
You're breaking up.
Yeah, this probably won't help, but if you try and remove the second video that you have 2 video feeds. Hello?
Okay. So let me pull out. Oh, I didn't actually put it. Oh, that okay. I have to put child remove.
Well, I mean, I could probably. Can I do it? Well, I just kick it from the studio. Do you want me to do that? Okay, so you have that as a.
I think you are.
Okay, I'm just gonna.
Yeah, on the side. I think this will prevent feedback.
Okay. Okay, fine.
Otherwise, I will remove it. But when we talk about that, yeah.
Okay, so let's look at the definitions here. In physics, symmetries are transformations that leave the laws of physics unchanged. Okay, so we know this is all quite straightforward. All right, so the 2 types of symmetries we're discussing are global and gauge. A global symmetry is a symmetry that is present throughout the entire system. So anytime you want to comment on any of these points, just let me know. Meaning that the system looks the same regardless of the location or orientation. It is a true physical symmetry with an associated Noether current. Global symmetries are inherent properties of the system, unaffected by the choice of coordinates or gauge. Okay, so we probably need to unpack that sentence at a later stage. We'll remember to come back to it. Examples of global symmetries include
which one is this one?
Charge, conservation of particle number, example baryon number, spatial and temporal translations, homogeneity, and isotropy. So by contrast then, gauge symmetry also
are you reading from Wikipedia?
Yeah, I'm reading from like a summary of the two things, because I'm asking you for more clarity on this subject because I'm not that clear on it. So I'm just trying to give some background.
That's what I'm trying to decode. Yeah.
Okay.
Oh yeah.
Okay, good. So I'll continue.
I think we'll pick up after the 8th episode.
Sorry, what?
After the 8th episode, we will after the next episode I have prepared. I can show you briefly, but that's towards the end of November. Like the 24th or something. But so in between, we had time to discuss all that because this is where a lot of confusion occurs. We have to clarify that. Then 8th episode talks about Bell's theorem and things like locality. After that, we can design. I don't want to put the 9th and the 10th should be a clarifying aspect. You know what I mean? Clarifying that
this is still like we're just asking. So I'm basically saying that I don't fully understand this.
We will go over this today itself.
So I'm interested in just exact. Like I don't have a problem saying that I'm unclear on all of these points. So, but what I do, I have a problem. Like if we say we don't.
So let me.
Wait a second. We don't understand this, but we're going to pretend we do or something, and then, we want to make sure that we understand it. I'm just going to remove that video, see if it helps, because you're still breaking up. Okay, so it's also referred to as a gauge redundancy. That's interesting because you bring that word up a lot in your talk. So we'll get back to that as well. Right, it is a symmetry that arises from the redundancy in the description.
Great simple.
Hello, can you hear me?
So suppose,
wait a second.
Yeah,
I haven't. I'm just reading this. So Oh, do you want to comment on this? Actually, yeah, you can go ahead.
Yeah. So hold on. So one of the things is that.
So what do they mean by redundancy in the description of a physical theory?
All right. So let me go back.
Well, I suppose it's
redundancy. Okay, you can.
Maybe it's redundant because it's symmetry, is it? So if you keep rotating something, you get the same answer. So it's considered redundant in that sense or something. Okay.
So one of the things, mathematics.
Well, continue on because I think are we happy with that, or do you want to add something?
Yeah, I want to add about very simple. One of the ways I'm looking at a very simple way of looking at the the gauge one is a little bit complex, but one simple way is that suppose in the integral, right? Suppose I integrate something, right? You have a constant term that comes in, right? In integration. You know what I mean? Okay. So by differentiating that, you can remove that constant term. The constant term doesn't change the integral aspect. You know what I mean? So suppose I add, I add x plus c, right? C is a constant, right? So suppose I take a differential of that, the c disappears, right? So adding a constant really is like a redundancy. We are adding redundancy. You know what I mean?
Oh yeah, but what does that have
you can remove that. So the same way multiplication. You can use
C in that sense some sort of is it a symmetry? Because you were using it in a physical sense before.
So suppose I shift the coordinate, right?
Yeah, I'm gonna remove your video because so don't put it back on, yeah. Okay, go ahead.
Okay.
Yeah, that's
okay.
So
I'm doing that so I can see what's going, but that's okay.
Okay, I just think it might be interfering with the
So the
Because
question
everything's
is, yeah, now it's removed, right?
yes. So don't put it back on.
Now it's removed. Okay, should
Okay.
be okay.
You can
Yeah,
put it
yeah.
back on
Okay.
later when you need it.
Uh, so
Okay.
yeah, 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 yeah. No problem. Thank you.
Okay. So right. So that's
Yeah.
interesting. So
So
because
the
you were
question,
using that before, weren't you?
the question
The
is, what
C
is
and
gauge? What is a gauge theory?
yeah. Okay. Have you frozen or something? Are you still there? I think you frozen, Rajan. Um,
Let me see whether.
okay. You froze there for a second, but you're back.
Let me. Can you hear me?
Yeah, I can
Can
hear
you
you
hear
now.
me now?
Yeah.
Hello. Okay,
Can you
good.
can you hear
Because
me?
I cannot see. That's why I was getting the other one so that we can see. That's okay. Because when I
What do
put
you
this
need to,
on,
sorry, what do you need to see
I
on
cannot
the
see
other video? What do you need to see on the video? Your notes, is it?
that what our video, your video and my video. So, but it's okay.
Okay, good.
I'll just go
Right.
on, till we finish this.
So
No
what were you
problem.
saying? Local, what is a
Um,
local symmetry or something you were asked? Or what's a gauge symmetry, I think you asked. It's a pretty fundamental question, but that's where
yeah, gauge theory.
we're at.
What's a gauge? Yeah.
Theory, right.
So I think that is still, yeah, it's not very clear. So according to the literature, the gauge. So I want to what the literature says before we interpret, but we should interpret, I think, because it's a little bit confusion about a gauge theory is a field theory that's unchanged by its certain local transformations. What these local transformations is that gauge theory is based on Lie group. You see that? That's why I put up. So if you go back here, I put a here. So
Mm,
this is connected very closely with the SUN group and things like that. So the Lie algebra, right, is like SU2 is you have you know the quaternions put there, and the Lie algebra has a specific uh, you know consideration that uses the polymatrices and try to get a simple things that unitarize. It has a unitary thing, the 2 by 2 matrix. So it uses a simple thing. It's a high level symmetry, right? Lie algebra is a high level symmetry with determinant one. So the gauge theory tries to use that. So the gauge theory uses this Lie algebra thing, Lie group,
yeah.
symmetry group, or gauge group. So what it does is that it removes the redundancy, extra things it removes, like trivial solutions, trivial things. So little degrees in the Lagrangian. So Lagrangian has a lot of things that the movement, suppose a vector is moving to another place, the constants don't matter there. You see that you can move the so vector space, you can move from one to another without changing it. So translational aspect, but also the rotational, especially the rotational aspect, right? So when you rotate, you probably know a lot better than me about the rotational, in the group theory. But rotation things, when you go around, you only consider like 2 pi rotations or pi rotations. You don't worry about 2 pi rotations or 2 pi
Well, you might for the fermions, right? Or actually that'd be 4 pi rotations.
and
Okay.
or
You're
six
still
pi or 8.
yeah. Okay.
So we are looking at unique things remain same. That's the question that gauge. I think gauge in a way solves that problem, because
Okay,
it
you
considers
broke up. You broke
unique
up there a
things,
lot, Rajan. I don't know.
combinatorial things instead of permutative things in some
Maybe
sense.
try
So that is a way that
try
Maxwell theory.
to. Could you turn your camera off? I'll switch my camera off.
Is it off?
Yeah, just turn it
Can you
off.
see me?
I can, but I can't hear you because of there's a delay, or not. Well, there's a delay, but there's also you're like starting and stopping. You know.
Oh, let me look at that. Let me.
No. If you just go down to the bottom of the StreamYard app and hit stop cam.
Yeah, for me to access that, I have to go here.
Okay.
Let me see.
Yeah, just stop.
See, I have to come here.
No, down, left, or the other left. Yeah, there. Yeah.
Stop cam.
Let's see if that helps. Okay.
Okay. So let me see. But you have to tell me whether you can see me. I will see the.
The other thing is maybe to switch off as many programs that you have running in the background as possible.
There's no other program really.
Okay, good. Well, so you were talking there about pi rotations, 2 pi, and so on. Correct?
So let me. Again, I have to reset. Sorry.
No problem. I'm gonna have to go in a few minutes.
Okay.
And then I'll come back. But
Okay. So let me. Okay. So I think you can see. Let me go back to the slide. So this is the Lie algebra. Something something you have to really. So I want to look at it again. These things I just presented in the way so that we can expand on each one. I think we are doing that today, but I think there are a lot more clarification needed. I agree with that. Because we have to really go to the bottom of what really is gauge theory, what really is global symmetry versus local symmetry. I think there is a lot of confusion about these things. So
yeah, I think you're right. I think
we have to spend a lot of. We have to spend. We should concentrate on that and probably spend a session or two on that, looking into more detail about this. I agree with that. So you look up your side with the Wikipedia, different things, and we clarify. We'll go over how to dissect these things. I like dissection in that sense, that decode the things and then get a clearer picture of what it is. It's not very clear for me also. So the gauge itself is removing redundancy. So I would think that when you rotate, right, you get a lot of extra things. So you want to remove that. So that's one more thing gauge. So for example, Maxwell equation, you have the electromagnetic, the magnetic thing creating the electric things, and the electric things creating magnetic things. But in terms of the gauge theory, what's happening is that these two are combined together. So you can use a general field to describe either magnetic field or electric field. So this is what gauge theory is claiming to be. And we have to look into that, whether it's actually doing that or not. I'm not so sure. But some of the tensors, I have put it out in some of my publication also. I put some tensors, what they have put it, and then using that tensor, what you call the four field tensor or some things like that are there. Using that tensor, you can describe both electric and magnetic field. So this is a claim, but it uses a differential tensor calculus, differential calculus tensor uses a tensor form of the whole field. And then it is because Maxwell essentially used only vectors. He didn't use tensors per se. So rank 1 tensor, but the gauge theory is making that vector into a tensor. that I think is a good thing, because tensors can describe the whole thing, in a better fashion. But Maxwell uses a vector, so it's simple in the sense that it's more measurable. See, when you go from vector to tensor, higher rank tensor, it becomes more and more immeasurable. It becomes more theoretical. So you have to bring the rank down to vector at least. And I'm actually concentrating a lot on that. Also, I have like a few publications coming up. I think I briefly talked about reference points in some point. So we don't have a proper reference. For example, I'm measuring length. Actually, it's a vector. So I should describe what a reference frame is. So so I come up, one of the publication I'm going to come up with what reference we should be using. For an electron, we have to use photon, things like that. So proper reference frame, we don't have that now. I think that's one of the things where the measurement problem comes from. For length, we use a standard measurement, right? We have a standard put in Paris or something for length measurement. It's described by expansion or something. So we can look into that. What the standard of the length, what reference point we use for length. For example, I use a ruler, right? So ruler, but ruler in a general sense doesn't really give the correct length measurements. So again, you have to use a proper reference point. For mass, for example, you have to use gravity. What gravity we use? Gravitation of the Earth or global gravity, things like that. So again, you have to describe a reference. So I'm coming about for different things, what reference point we should. So that's one of the key things, the reference frame. Let me put it, just a reference frame. And I think gauge symmetry does generalize that reference. So if you move that, suppose I move something in vector space, it doesn't matter. So I can put a vector here. It's the same as a vector that is displaced up and down. Okay. So the vector has a property that if it is describing one part in space, it can describe another part in space. I think that's one of the reasons. I think if you look at the what you call the quantum entanglement superposition, that's one of the reasons, because I can describe a vector here and I can shift it up in space or this thing. The actual vector doesn't change. So it is the same vector. So I can say that I am here, it's the same. Okay.
Okay, so let me just interrupt you there.
Okay.
To clarify, when you're talking about the vector, then is it the vector is is it part of group theory? Is it local or is it global?
Yeah, it's an interesting thing. So that's what I'm trying to dissect. So the vector, I think the gauge theory in some ways implies that. It doesn't talk explicitly about that. You see that we have to look into more literature to see somewhere, are they talking about that? I'm sure they're talking about vector space. They're talking Hilbert space. They're talking about vector space. See, these are very important concepts in there. For example, Hilbert space is a very important thing. And there are other spaces also, Banach spaces. I did a little bit.
Yeah, but just like we just want to focus on the topic.
Yeah. That's what.
Which is what?
So
we're talking about local or global, right? Gauge.
Yeah.
Global. So so that's fine. You want to I don't know, reduce the tensor so it's a vector.
Yeah.
But then you seem to be using it then as a global symmetry or something after that, once it's a vector. Is that allowed?
Yeah. So the vector, you can move it in space. It doesn't change anything, right?
So you're saying that you can alter maybe a local symmetry into a global symmetry.
Yeah, that's the thing. How you can globalize.
Okay, that's another thing that would need to be.
Yeah.
How do you say, like, justified or something?
Yes.
And I think before we can justify anything like that, we probably need to know what we're talking about.
Yeah.
A bit more.
I agree. So, again, it's okay. Sorry.
I'll just go back to this then. Just reading this thing for a while. Make some points that are interesting. So in gauge theories, they're not true physical symmetries, but rather a consequence of the mathematical structure of the theory.
Okay.
So if you look at the standard model there, you've a non-abelian gauge theory with these symmetry groups. So it's saying that they're not true physical symmetries, but are a consequence of the mathematical structure of the theory. Well, the mathematical structure of the theory here are the groups, the U1, SU2, and SU3.
Yes.
Okay. And those are the symmetry groups of the gauge theory.
Yes.
So none of those are true physical symmetries, it's saying.
Yes.
And that's a bit odd, isn't it? Because U1 is supposed to be the physical symmetry of the electromagnetic force. It just goes around in a circle.
Field, So
that
the photon, right?
Yeah, so that's interesting the way you have it written out there, because U1 would be the photon.
Yeah.
And then SU2 gives you three vectors, or three matrices.
Weak boson.
Then you get the weak boson. So presumably one is a plus
W plus.
W plus, one's the W minus, and then
Z.
The Z boson is in some sense a coordinate, I believe, between the U1, which is on the Z axis, and then the W boson is on the Y, and the other W boson is on the X axis, and then the Z is kind of just a coordinate in that space. That may be a bit more overcomplicating things, but then we have SU3, and that's got 8 of those, those matrices, 3x3 matrices with determinant value 1. Okay, but they're kind of weird because you're in general. Well, anyway, we won't get into that. But yeah, you have it there later on. Note SU2 are 2x2 matrices. They have 4 elements, and one is unitary. So does that not mean that the unitary one though is not the same as U1, is it? Because U1 is
no. So that's why you have 3. You have only 3 weak bosons instead of 4, because one of them is just 1. So you have only 3. Although there are 4 elements, one of them is always a unitary. Just 1, just represent unitarization aspect. So really, the physical things are only 3 weak bosons, although there are 4 elements in a 2x2 matrix. You know what I mean? So 2x2 matrix has 4 elements.
Yeah, but it's not. Wait a second, though. There's 4 elements in a 2x2 matrix, all right. But I think the point is that they're making is that there's 4 elements in SU2, including the unitary matrix.
Yeah, but there's only 3 weak bosons. In the SU2, there's only 3 weak bosons.
Yeah, because one of them is kind of redundant, right?
Yeah.
Okay, so I thought that's very interesting anyway. In gauge theories, the symmetry group acts differently on each point in spacetime, introducing redundancy in the description of the system. So this redundancy is eliminated by imposing the gauge condition, which fixes the freedom in the choice of the gauge. Now, what can be said about that? Imposing the gauge condition.
Okay, suppose you take, interesting thing is about a general relativity itself. So if you use the general relativity, the gauge field is a tensor called Lanczos tensor. It's a rank 3 tensor. So it generates a Weyl tensor, which measures the curvature of the space. So it's a non-degenerate. You see that the problem is what gauge theory is trying to take it out is a degenerate things. The degenerate of energy. So it removes all that things. So it creates only non-degenerate.
What do you mean? When you say non-degenerate, you could say, well, that could be to do with a physical thing, like the energy doesn't degenerate, or it could be like a mathematical kind of terminology to do with like I don't know, like matrices being,
Yeah,
this is a symmetric matrix, this is a non-symmetric matrix, this is a non-degenerate matrix or something, or a non-degenerate tensor.
yeah.
So what does that mean?
Okay. So what it is trying to do, the gauge theory is saying that it's trying to somehow try to cement between the theory and measurement, so it comes on in between the thing to connect the theory to measurement somehow. That's why I feel it. So when you actually measure something, the degenerate things don't have much meaning, because they all like degenerate energy, for example, which is like redundant things. It's a repetition of things, but in a measurement it kind of removes by itself. So gauge theory is saying that, okay, when you measure it, you don't see that degenerate thing. It's a creation of the math. So it is a math, because you see that gauge theory, the graviton is a mathematical thing. It has not been proved, right? But the gauge boson is actually a graviton. So it advances the mathematical theory of the tensors, and then it says that this rotation should produce in specific things in 2 pi rotation. If it has type of spin it has, it should create a graviton. Spin 2, gauge boson should be a graviton. That's what it proposes, but it has not proved that. So that's the gauge gravitation theory, right? Advancement. But the bosons itself is looking at different ways. So the bosons, uh, you know, bosons, how does it look at the bosons? Is that it looks from the spin aspect. So the gauge theory tries to get into the idea of the spin itself. So it is that aspect a little bit confusing for me, but the gauge principle of covariance. So there is a covariance in general relativity. Covariance essentially, you can say tangent plane kind of thing. So it looks at the tangent plane. So you have a field. Tangent plane is the movement of that field. Like you have electric field in the x direction, uh, magnetic field in y direction. Then the c direction should be the motion, right? How it moves. So that's like the tangent plane it's trying to create, but in a more curvature. So it takes into curvature and everything. And the general relativity actually tries to generalize that, the Maxwell thing. Uh, so it talks about the tangent plane where things move, real things happen, the motion happens. So that's where the covariance in some ways come into picture. And so gauge theory looks at that. Not all of the things in the x direction, not all of the things in the y direction will automatically create the motion, right? So there is a lot of extra things. The gauge theory says we have to remove those things. So
Oh,
that's a complex way that the gauge theory is looking at, you know. So
okay.
mathematically, it's a
So I think
mathematical treatment.
that's pretty good. That's interesting. I think what we can do is take a short break
Yeah,
here, because I have to remember I said I have to go and get this stuff. So I'll be back in about few minutes, but we want to take about a 10-15 minute break or something.
yeah,
10 minutes. Okay, cool. See you
yeah.
then.
Maybe like even 15 minutes is okay.
Okay, cool.
Okay. So we'll back in 15 minutes. Okay, thanks.
Hello?
Hello, are you there? Yeah,
Yes,
we
we're
can
back.
continue. So I'll put the slide back in. Yeah.
I see you had three astronaut ladies.
Yeah,
Was that
let me put the. Is it okay? I mean, the is it coming on the slide?
Yeah.
So let me put it back and then. Okay. Each time I have to remove the hide the person. That's okay. And subtitle also. Okay. Okay. So now we were. Yeah, I think that's a gauge theory thing. I think. Yeah, I think
Yeah.
if you simplify that, yeah, what always happening in the X direction or Y direction doesn't automatically translate to what's going to happen in the Z direction, something like that. So the gauge theory tries to see that's a Lagrangian, right? Lagrangian talks about the motion, the dynamics of the motion. So it says that Lagrangian has a lot of extra degrees of freedom in that sense. But whatever is happening, it's not happening there. So the Lagrangian contains a lot of extra things or redundant things that the gauge theory removes that by using. So that's the claim of the gauge theory, you know.
But isn't right? So there's. But I thought from reading this, it was saying that there are a lot of redundancies in the gauge theory.
Yeah, the gauge theory itself may have, yes.
Yeah,
That's
like
quite possible.
that's why they're called gauge redundancies.
Uh,
But okay, so how I'm thinking about this, yeah, during our break,
uh-huh.
I was thinking that right, so you have the global symmetries and then you
Uh-huh.
have the gauge symmetries. And
Uh-huh.
according to this, it was saying that the gauge symmetries, okay, so they're eliminated by the gauge condition. So maybe that's what you're talking about.
Yeah.
But they're so it's a local symmetry, meaning that it varies from point to point within the
Uh,
system.
uh,
Now, do you think that that's just that comes from the concept that we're dealing with a quantum system? So, like we're going through differentiating or something, and over space time,
uh,
we look at a small point in space time, and that's
uh,
going to be a quanta, which is a particle,
uh,
and so that's going to have a gauge symmetry associated with that particle,
okay.
or more, yeah, or several gauge symmetries maybe,
Uh,
and then so that's going to be different to the global symmetries somehow.
uh.
Does that
So
make
one other
sense? Do
thing,
you think that's what you're talking about?
yeah, one other, yeah. So let me clarify. One other things is that, uh, for example, the photon, right? The photon has automatic kind of global symmetry because you can get light from light years away from other side of the universe. We can get it here, right? But that's not true of gravity. That's the idea. So photonic aspect or electromagnetism is more global symmetry in that sense, whereas the
Wait a second.
gravity,
Then. Doesn't gravity have an infinite reach because it's also
no,
a force?
well, that's the whole thing. I mean, it's actually a local symmetry. Create, for example, a black hole. It's a local thing, right? But it has reach over global thing. Whereas the electromagnetism, it can transmit automatically, right? Globally. I mean, almost supposedly, maybe instantly, according to Newtonian thing, almost. But normally, because of the vacuum and the, limit of the speed of light,
How are you saying
general,
no? Like electromagnetism moves at the speed of light, doesn't it?
yes. So the speed of light, but the thing is that it could have some kind of, monopoles or something like that that comes later on, may have almost instant things. I mean, it doesn't have speed limit. It could be superlumina.
Okay,
So
that's going outside. That's definitely going out. Like we're just trying to deal with the basic. Well, I
yeah,
wouldn't call
yeah,
it
yeah, yeah, yeah.
basic.
I agree. I agree. So electromagnetism with the speed of light by itself has global symmetry in that sense. But as gravity is created by a local entity like black hole or anything like that, and then it has kind of a global outreach. So it's actually a local symmetry that has a global outreach, whereas the electromagnetism has a global symmetry that has a local outreach. So it's kind of very simple way looking at it. So the global symmetry affects how the global symmetry of the electromagnetism affects the local things, versus the local symmetry of the gravity affects the global things. So you can differentiate the global symmetry and local symmetry. That's what Swampland conjecture is trying to do, I think, in a way. I don't know whether I don't know. It doesn't have, it was promising in that sense, but it has a lot of problem that we can look into, that went into later on loop ground quantum gravity, other things, because it uses they use all these Swampland conjectures, string theory, and all that, and then put them together. This was what all the five symmetries of the five different string theory. So that's the M theory. M theory is trying to do that. The brain is trying to put together all these, bring all these to same platform, same page somehow, and then try to solve the problem. So the M theory has, more compact, more what you call a grandification aspect than other theories. But I think it also has some problem. That's why brain theory, or everything has limitation, and there are, when you go into detail, the devil is in the details, so to say. When you go into details, there are problems, and the same thing, because everything now depends on general relativity on some sense, quantum, and we are trying to put them together, you know like apples and oranges type of
Yeah.
thing. So I think that's where a lot of the problems. So
Okay.
these things.
Well, yeah, that's a fair point. I mean, so it seems like, yeah, because you're talking about gauge bosons and stuff there when you bring up the photon, let's say. Now, and that's different then to a fermion, for example.
Yeah.
But the fermion also has a gauge group. So,
Yeah.
but we say that gauge bosons correspond to a gauge group. In some ways, these bosons emerge out of the group somehow. I read it there earlier. I'll just look for it. There's an interesting thread that I was looking at, and it had a lot of concepts in it that I don't really understand. So that I'm just newly being exposed to. So I'm going to try and search up as many of the terms that I can, maybe during this live stream, and we can go through it and see if it helps us understand better what's going on.
Okay.
So we have, so they're talking about here electric charge weak. Now, see, the problem with threads online, people just discussing, you might have two people arguing on a subject, yeah, and like they disagree. So one of them is wrong, let's say, and the other one is maybe right or knows more about certain things. So so the problem is, if you're listening to someone's what they're saying and you take it as gospel or something, that could be. So that's why we'll just read out what they say and then we can go check it afterwards.
Okay.
Okay. So the electric charge weak isospin hypercharge relation in the electric weak theory. There are conserved Noether currents in the original theory. Now there's that term Noether currents again. That is obviously a global symmetry, but
does Noether imply global symmetry?
I think so. Yeah, because the gauge groups don't have Noether currents, apparently. Now, I did look into. I've come across this Noether current concept. Well, looking up Noether's theorem previously, and I thought it did have something to do with like more quantum kind of stuff.
Oh.
Through the wave function normalization or something. I was kind of led on to that aspect. And I got from the Ward-Takahashi identity, which is related to Noether's theorem. And it's all identity of quantum electrodynamics, QED. So, and it's related to this wave function renormalization of the electron to its vertex renormalization factor, whatever that means, guaranteeing the cancellation of ultraviolet divergence to all orders of perturbation theory. Later uses include the extension of the proof of the Goldstone theorem to all orders of perturbation theory. So you have more generally a Ward-Takahashi identity is the quantum version of classical current conservation associated to a continuous symmetry by Noether's theorem. Such symmetries in quantum field theory almost always give rise to the generalized Ward-Takahashi identities, which impose the symmetry on the level of the quantum mechanical amplitudes. This generalized sense would be distinguished when reading literature such as Peskin and Schroeder's textbook. All right, okay, so I've read that textbook, parts of it, and it's quite good, but it gets a little bit technical, and you know, it's not like you don't feel like you're reading it and getting I don't know, an informed kind of concept. It's just it feels quite bitty, you know. It's like, oh, there's this bit over here, and there's this bit, and yeah, we're not telling you how they connect because either we don't know or. But anyway, so this whole Ward-Takahashi, I assume I'm saying that right, Takahashi identity. Yes, identity seems to be like all very much on the order of the quantum. So, so obviously, just because something is global does not mean that it's not quantum. So maybe my earlier attempt to make a distinction between a global thing and a local thing being quantum and global being more large scale is incorrect. So, and I would say that that is probably right. Once it undergoes symmetry breaking, the charges corresponding to the residual symmetry with the appropriate gauge bosons that didn't. Okay, so I'm just trying to look for the point that they made about bosons. Because that was kind of interesting and I didn't really understand it. But searching for the term boson. Oh yeah, here, maybe this is it. Right. Okay, so the original thing was not sure what globals. Right, a simpler theory, SUN, okay? Now, it's N, so they're saying, you know, it could be any number in there, which is weird. And then Yang-Mills, which is something I hear about a lot. Are there U1 subgroups of SUN? And he says that there are plenty, but the other guy disagrees with him later on. So adding one flavor of quark to the theory, there are now U1 global symmetry transforming the quark fields while leaving the gauge fields untouched. So now, why would a quark have U1 global symmetry? Aren't they? Isn't a quark SU3, or is that just how they interact with one another?
Well, quark, but SU3 has gluon, right?
Yes, that's a good point. But don't the quarks like interact? So you have like up or not the different flavors of quarks, and the antiquarks interact to create the gluons, and then the gluons have an SU3.
But you need color charge, right?
Yeah, true. So this is talking about a flavor of quark. So a flavor actually is not to do with color, it's to do with the generation, isn't it?
Yeah, flavor.
Whether it's top or
More mass aspect, right? Flavor
right.
is,
Okay, but so why? So they're saying that a quark has U1 global symmetry. Okay, so it's equivalent then to an electron, or not an electron, but a flipping a photon.
yeah, actually UN is more like a vector, right? So it means that
U1
you have
is
different.
U1, like, so the
No,
unitary.
U is a vector, right?
Well, it's a matrix.
Yeah, but it is a vector, more of a vector.
It's not. Well, it's a circle, isn't it?
The circle.
It's a circle.
Rotation. So
Yeah,
rotation.
it just goes round and around in a circle. It's just a transformation that rotates something in a circle around around a point, an axis point.
But this means that there are different types of rotations. UN means that you can have n different types of rotations.
This is U1. One.
Yeah.
Just the number 1.
No, UN.
I know, but this is just saying U1.
U1. Oh.
Yeah. So U1 global symmetry, transforming the quark fields while leaving the gauge fields untouched. And there are physical states, baryons with non-zero values of charge. Whatever the mechanism is for breaking SO10 or whatever, down to SU3 cross SU2 cross U1 may be, resulting U1 charge conservation is related to a global U1 symmetry. Now, we have a global gauge symmetry. Now I'm getting confused. Of the underlying
building upon
U1 symmetry of the underlying matter fields. Very good. So now the response. Again, I have to point out several things which I do not understand with your reasoning. There are U1 sub. Now he's quoting him here. Did you want to say something before I go on, Rajan? Because I'm just moving quickly ahead through them.
Yeah, the only thing I want to talk about the global gauge symmetry. So it is combining the global symmetry, which is kind of a Noether's thing,
right?
The gauge theory, which is like a group thing, right? More like
yes.
Okay, so it combines both the Noether term with the group theory kind of thing.
Presumably, well, I assume they were going to be separate, but here, I suppose maybe if we remove the redundancies, and I don't know, maybe they can be reconciled at some point. But then why? Then I would assume that there would be no reason for the distinction after a certain point. You know, they just throw out the distinction, but maybe not, because scientists do tend to like categorizations, even if they don't actually do anything. Let me actually that's one thing that we should consider. You know, sometimes like when I'm working in okay, so it's a bit like if you're driving your car, yeah, and I ask what gear are you in, you might have to look down, presumably, you know, because you didn't think about changing the gear, you just changed it. So it's a bit like that, you know, like I could be like, oh, well, it's very important to know what gear you're in. And you might say, well, no, it isn't actually. I can drive around all day and not know what gear I'm in, you know, and I do just fine. So similarly here, you could be like, well, is this a global or is this a gauge theory? And it's like, well, who cares, you know, maybe it just doesn't matter. Like, but so I find that a lot. Now, I'm not saying that it applies here, but I'm just saying, I've noticed that in certain things where people are like, well, is this an unsupervised or a supervised machine learning model? And it's like, oh, like people say this, I think, in order to sound like they know what they're talking about. But when you're actually doing the work, you really don't care. Right? You just do it. You know, and you have to think about whether it's supervised or unsupervised or whatever. Then you're not really doing the work. You're just thinking about categories or something. Anyway, okay, let's move on. I think I've already mentioned that before, actually. So, that's the end of the rant. Let me preface this with the following. Okay, so he quotes, he says, are there U1 subgroups of SUN? Yes, plenty. Charges are representations of the group. You're asking whether an SUN theory contains U1 representations. The obvious answer is no. Why would it? It contains SUN representations. Okay, I mean, that sounds good. What you're confusing is charges and charge carriers, i.e. gauge bosons, aka the adjoint representation. Now, that's a very mathematical, technical term. Well, not very. I mean, it's a simple enough thing. But the adjoint representation of the matrix, right? So what's the definition of an adjoint matrix again? Or I assume it's like, it's what? It's not.
Is it a Hermitian? Not a Hermitian.
Yeah, it's something like that, right? Adjoint, or there's another word for it.
Conjugate.
Yeah, adjugate of a matrix plays a crucial role in linear algebra, particularly the calculation of the inverse of a matrix. So it seems to be related to the inverse of a matrix. Transpose. Wait. Oh, in linear, the adjugate of a square matrix A is the transpose of its cofactor.
So row to column to row, type of thing, right?
Transpose. Yeah, but it says of its cofactor matrix. So it's occasionally known as adjoint, although the term today normally refers to the different concept, the adjoint operator, which for a matrix is the conjugate transpose. Right, so you are correct, which is the Hermitian transpose. Okay, so it's good to know what we're talking about.
Yeah.
I was thinking when I read adjoint, I was thinking Hermitian, but then I was like, well...
Yeah, always. Yeah, I like to boil down to simplest concept, you know.
Yeah.
Always we should do that.
Oh, good. Okay, so why would it? It contain... Oh, yeah, sorry, we went over that. Which is uniquely determined by the group. Well, that would make sense, wouldn't it? That the Hermitian matrix is determined by the group. U1 representations obviously don't manifest as SUN representations because that's not the whole group. Now, that is a very straightforward statement. I agree with that. Not sure if this is really helping, but now when we break the group via a Higgs representation, then if the residual symmetry is U1, the gluons would become n to the power of n, maybe -2, heavy bosons, and a single photon. And that's interesting. Oh, so that must be the heavy bosons being the weak bosons.
W and...
Yeah, and even the Z, and then a single photon. So there's your SU2 group, I guess. Now when we break the group via the Higgs representation, although... Right, so the Higgs representation is breaking the group, I guess. I see absolutely no issue here. It's what we observe in the whole group. Okay. Moreover, SUN is a simple group, so U1 isn't a normal subgroup. That's true, and there are, in fact, none such subgroups. Interesting. I mentioned the normal subgroups because that's where you could argue that the charge carriers manifest as separate entities, since one can quotient out the adjoint representation in a meaningful way while preserving group structure. This is precisely what we see with the standard model group, which is semi-simple rather than simple. Okay, so lots of terms there. You lost me a bit at the end, I have to admit. Let me put forward another argument. SO3 is a subgroup of the Lorentz group. It's clearly its own representation with spherical harmonics. Okay, I didn't know that spherical harmonics had anything to do with the Lorentz group. Do we care about those in special relativity? No, not at all, because those representations aren't Lorentz covariant. Similarly, U1 representations aren't covariant. So it's just drawing a parallel there, really, which is great, but it's not that useful. Okay, gauge fields are unique. You can't have flavors of gauge bosons. They emerge from the adjoint action of the Lie group on its representations. So what does that mean? So if we take the Hermitian operator, and what do they mean by on its representations? The representations of the group, which are just the matrices, I presume? Could they be anything else? So if we take what does the Hermitian operator do again? Or the Hermitian transpose, like what
I
is
mean,
it?
try to get to the identity. It connects with the identity matrix. I mean, so if you have Hermitian times the original, you should get the identity.
Oh,
Something.
yeah. Good point. Okay, so that is what they're talking about. Right. So you get the identity. So you don't necessarily get a gauge boson then, do you?
That's the whole thing. We have to work out. For Cottonians, you may get. But a Hermitian, I don't think it works with Cottonian. I'm not sure.
Yeah, because well, what was the point that he made? You can't get so he's saying flavors of gauge bosons. Now, do gauge bosons have flavors? I thought flavors.
Mass. Oh, gauge bosons are mass, right? They have mass, right?
No, because they
no mass, massless.
Well, no, wait a second, because I was thinking that surely a photon is a gauge boson, isn't it?
A graviton is. I'm not sure photon is.
Well, a graviton doesn't have mass generally.
Yeah.
If it's spin 2, it doesn't have mass.
So I don't know. Flavor doesn't make sense.
Have mass. So flavors of gauge bosons. I didn't know that gauge bosons had mass or flavors.
It's a different. So it's a massive.
It can't
be a massive.
Yeah. You can't have generations of gauge bosons. You have generations of quarks and you know, leptons. But I've never heard of flavors or generations of gauge bosons. Have you?
So in this case, they have mass. They're saying that then it has mass. Flavor means it has some mass in there.
Okay, I've never heard that before. I did not know that was a definition of flavor.
Well, it's kind of trying to use flavor, the higher level sense, but the mass in the sense that it's imaginary mass. It may not be a real mass.
Okay.
Flavor. Cottonian mass. Maybe like a Cottonian mass. Then, you know, it's not.
I've never heard of a quaternion mass before, but let's just.
Negative. No, they're talking about negative mass, positive, negative mass.
He says, right, but he's saying you can't have flavors of gauge bosons.
You can't have?
Oh, yeah, but then if we read the full sentence, right, the next sentence, they emerge from the adjoint action of the Lie group. So when he says they, does he mean the flavors of the gauge bosons emerge? Okay, let's go back to the start of this sentence. Gauge fields are unique. You can't have flavors of gauge bosons. They emerge from the adjoint action of the Lie group. So it sounds like he's saying that the flavors of the gauge bosons emerge from the joint action of the Lie group.
No, you say they can't, right? They can't have.
I know, yeah. I know, yeah. The first sentence is you can't have flavors of gauge bosons. The next sentence is they emerge.
So no, it says that because they don't have gauge bosons.
No.
Only emerge
because they don't have flavors.
Yeah.
Because the gauge bosons don't have flavors.
They emerge from the.
There's no because. He's just making a flat statement.
They didn't phrase it correctly.
Have flavors of gauge bosons.
They meant that, but they're not explicit. They're not explicitly saying that. Yeah. So it is not a proper.
Yeah, because that's what I'm saying. Because in the next sentence, then he says they emerge. What's they? It has to be the flavors of the gauge bosons.
No, what he's saying is that they don't have flavors. So then how did it occur? So he didn't clarify that. He's not clarifying.
Yeah. Okay. So perhaps this isn't a useful avenue of research, but it is kind of interesting in some respects. Yeah. So they emerge from the joint action of the Lie group on its representations. Okay, so maybe I'm not sure. When I read that first, I thought it was more like profound and more clear. But the more I'm reading that, the less I understand it and the less interesting. See what I thought? I thought he was saying that if we take an adjoint action, so if we take the Hermitian operator or the Hermitian, whatever it's called, action. That's of these two Lie group representations of these two matrices or whatever. you get the gauge boson out of it, showing that, oh, these connect with this gauge boson. But I'm not sure if that's what he's saying, and I don't think that that is what that sentence means. So we can move on.
Not clear.
I was just reading it going, oh, right, there's quite a bit about this subject that I don't know, because they're talking about things that I've never even heard before. And now that I'm reading that, I don't even think that's what they're saying. And that's a good thing, because that means that we don't have to worry about that. That it's not a thing that needs to be researched. Now, the language here is pretty crude, so I'm going to skip over that. Exact same symmetry you had assumed. Okay, so that's pretty good. Is there any other interesting points in this thread? Someone recommends a paper, but it's not very useful. Look up Elitzer's theorem. Never heard of that, but I'm not going to. Okay, well, can you find any proof that a flavor refers to mass?
We have to Google it.
Yeah, that's what I wanted.
You can ask, is flavor, does flavor means, does it refer to
mass?
Yeah.
In a, like in a general high level sense or something?
Yeah.
I don't see how it could, because I mean, obviously the three particles are heavier as you go up in generation, but it's not the mass that is the like, okay, the difference between them is mass, but mass is like, is in lots of
so muons, right? It makes sense. Like muons, it makes sense. You know, tau, muon.
I don't think it does make sense. It seems very like, if we were to use the word flavor to denote mass all the time, then why don't I say, well, what's the flavor of the moon? And you would say, oh, it's
no, whatever. That's because real. Mass is real. Flavor has both real and imaginary, complex thing.
I've never heard of complex mass or imaginary mass before.
Let me see. Okay. Let me see whether.
I've heard of imaginary time, all right, but never imaginary mass. Rajan, I have to go back to get my clothes out of the machine.
Okay.
Because they weren't dry the first time. So
okay.
You have fun and share your screen and share whatever.
So you are going off?
Yeah, I have to go down and get my clothes. But
are you coming back?
Yeah, but that's why I'm saying, you know, share your screen, or, you know, show different do what you want, essentially.
Okay. But you will be back 10-15 minutes then?
Yeah.
Okay.
Okay, see you soon. Bye.
Okay, thanks. You see, yeah, the flavor physics. Okay, refers to the species of elementary particle. Okay. Particle physics. Okay. So here is okay. Let's see. Excuse me. Point that okay. Action of the weak force allows the conversion of quantum numbers describing mass and electric charge of both quarks and leptons, one discrete. This is not a flavor change. The mass and electric charge, the flavor states may undergo quantum superposition. Okay, so flavor symmetry, carry lepton. Okay, okay, yes. 6 flavor quantum numbers for lepton, electron number, muon number, tau number, corresponding numbers, neutrinos. So these are conserved. Your number in bosons, electric charge. Right. So the flavors essentially means that just both charge and the mass. So the flavor change means, or flavor transmutation means that you have a conversion of quantum numbers describing mass and electric charge. So the mass and electric charge should come into the picture for flavor. It's interesting. Okay. Strange. You're trying to dissect these things. See, you can simplify understanding of what it is really. Right. So we have these aspects. That's coming into picture. Let's see whether we can simplify any further. What we are talking about. All right. So maybe you can look into this aspect. This one. Let's look into that. Okay. So let's look into All right. So we look into so if you are looking here, kind of gives you an idea of the next level type of research that's going on. And showing here is essentially a sense aspect that comes into picture. This is kind of an ongoing research right now, but mainly we are trying to understand, for example, the coordinates, how the coordinates come to picture. See, both, especially general relativity, talks a lot about the coordinates, right? So the coordinate axes are important. We come to the reference aspect later on, but uh, if you abstract the geometry, then we have x, y, z. So the x-axis could be time, and present thing is that it could be a tensor. Time actually a tensor, probably rank 6 tensor, which can be degraded into vectors. And then the y-axis. So if this is the x-axis, then the y-axis here could be the space, and the z-axis could be the sense. So you have the xyz in this kind of a setup, more Euclidean in that sense, but it extends the Euclidean to higher dimensions. So if we start with sense, then we come from sense. Uh, it should be a rank 2 tensor because sense has both positive and negative, but also clockwise and anti-clockwise. So it should be a rank 2 tensor, and then you have we can degrade that rank 2 into the vector. So it's an O. You have to say O equal to 2 to 1. Okay. So I can do a tensor. If I have a tensor or tensor, I can probably split it into O1 tensor, O1 vector times O2 vector. So this is the idea of rank degradation. Because it's rank 2 I can do this way. Okay, for space, it should be rank 4. So for space, I have R2, R4. So the tensor becomes R1 vector times R2 vector times R3 vector times R4 vector. So then I can do n equal to 4. I can degrade this R1, R2, R3, R4. But one of them, suppose I say is one of them is time, then I can make into the Euclidean, what we see XYZ of the space. For time, it is rank 6 tensor. So I have t to the power 6 rank tensor, then I can convert into uh, the vectors t1 times t2 times t3. It should be something like that. Vector. all the way to T6 vector. So this is the idea of rank degradation aspect. A tensor into a vector space, vector field rotation. So I can say if you do a dimensional analysis, we can say a time, sense, and the space they can combine together, and I say t to the power n is a rank m tensor, or it has m dimensions. Ranked dimensions are kind of interconnected. Then sense, I can say sense I can describe by a signal to noise ratio, and that is O, rank O, and we know that it's rank 2. Then times the vector product of the space, which is rank x to the power n. So then I can add them together, the R space, the R, the rank space, or the rank category, into m plus O plus n. So if you do that, we can say an expanded dimension, because sense has 2, then space has 4, and the time has 6. I can say that it is 12. 2 plus 4 plus 6 is 12. So expanded dimension will be like 12. Then I can shrink that dimension, because I can reduce the sense into a vector of 1, right? So I say I associate positive with the anti-clockwise and the negative with the clockwise. So I can just say positive and negative in that sense, and I get I get I so I get so I get positive and negative. So I get just one, right? One vector one. So a vector should be sufficient to describe a sense. Then I need for space I need x y z, three vectors. That's a contracted, a shrunk space. And then time only consider one dimension. So altogether 5. So that's the minimum I need. So this idea of 5-dimensional space, Kaluza, Klein, things like that, talks about, and the space, time, and sense. In that sense requires that. Okay. So that is the main thing. And then you have scalar time. So the vector time connected to scalar time, we can do that operation. I'm not going to go into detail about that now. So that is one of the key things about the coordinates itself, the sense, time, and sense, space, and time, or time, sense, and space, whichever way you want to look at it. So the independent thing could be the time, that the space evolved from time, if we say that, but the sense may be there all the time. Although from the real space we project sense in the c direction, the sense could be the most fundamental of all of them. So, for example, superluminar uh, condensate, noisy condensate that we think is the whole universe is made up of, uh, then it has probably sense in the sense of the monopoles. They have sense, north and south poles. That's about it. But that from there, the hot PDP mechanism, we can get the real space, the time first, and the time then occurs in the form of wave functions, tensor wave functions, but they collapse and they create the space. So this is the general idea of uh, Okay, hello.
Hey, how are
Are you
you?
there? Oh yeah. So I'm just going through some new thing. I just put, I was just going through that. I mean, just describing that. I don't know how clear it was. The when you are
Yeah,
gone.
I got some of it. I heard you were
Yeah.
saying about, you mentioned the sense field or something.
Yeah, the sense could be there in the supraluminal thing, like north and south monopoles.
Well, what
So
is
that's
your
about
definition of a sense?
sense. Yeah. So I am putting that category. Sense is like positive and negative, right? Sense clockwise, anti-clockwise. In terms of translation, it's positive and negative. In terms of rotation is clockwise and anti-clockwise. That's it.
Oh, okay. So it's not to do with it's right. So it's a fairly straightforward so
Straightforward. Yeah.
plus and minus being like matter and antimatter, is it? And then
Yeah, like electron, positron type
all
of
right,
thing.
and then right and left. So why so really you're just talking about right or left-handed matter or antimatter particles.
Well, positive charge, negative charge, for example.
Yeah.
That's kind of thing.
So
And then rotation. Rotation may be where you have the chiral, uh, the
okay.
left-handed, right-handed come. So there also you have sense. You have left-handed, right-handed, but that's more rotational aspect, right?
All right, because I've heard you were talking about this sense field for a long time, but I never
Yeah,
asked what you
that's
meant by
the
it.
physical. Yeah, in
I
the
just kind of assumed because for a long time you were talking about audio and visual and stuff like that.
yeah. If you extend that, the things that we are talking about, what you call core physics, or just the what you call that plain physics, then you are positive and negative. But if you extend that to more exotic physics, that becomes more, or IT physics, if you say, then it becomes audio, video, and all that comes into
Uh,
picture.
yeah, I'm not sure. uh, um, it's like, well, there's a big thing. I was listening to a podcast there recently, and they were saying, the work that Newton did on light, for example,
Uh-huh.
and so obviously we see colors and things like that, and Newton did a lot of work into color theory, but I suppose at one stage, maybe during the in a natural philosophy sense, maybe they were considering the world from maybe a more subjective point of view about like how
Ah,
we see things and how we
yeah.
smell, like smells, touch, tastes, and all of that. But I think with Newton, when Newton came along, he was like, well, he was looking at it from a material point of view, and he was saying, well, the light is a kind of matter, so he had it as corpuscles, and that was the underlying thing,
Ah, ah.
So this our sense of the world is just a like a higher level thing, but deep down, what we're looking at is a material kind of world or whatever. So
Mm.
yeah, but then that's not to say that you couldn't, bring sense into it in some sense. But I'm just not sure of what you're doing there. I mean, I suppose it could relate back to what Newton was talking about.
Yeah.
I suppose you'd have to go from your, you know, your matrix here, which presumably has more matrices inside it. So it'd be some
Yes.
sort of tensor, and
Yes.
then right. So you go from that, but then how would you bring it up to the level of? Well, you see now when you mentioned video, that's where I had a problem because like video obviously is a technological um,
Yeah.
advancement,
So
if you like. So,
connect the so for example, video is connected with our visual thing, right? It's a eye
okay, so why not just
visual
say vision then? Why say video?
vision. Video in the sense of making the system. See, which I say vision, it is organic system, right?
Yeah.
So when I say video is generally inorganic or system description. So people description versus system description. We know.
Okay, so as people, we, you know,
Yeah, visual.
generally we can see
Visual.
or we can
Yeah.
hear. Okay,
Yeah.
but are you saying that there's something there's another type of vision that is non-biological?
Well, if we make into system level, right? IT system.
Yeah.
Right now, IT system is not organic yet. It's still inorganic, I would say.
Yeah.
With the robots, with the future thing, they are even coming out tongues, you know, robotic tongues and all that they are coming up with. So
Yeah.
you may have sense of taste and everything they are putting to robots. But right now it's inorganic, like all our things are bytes and bits and bytes and all that, right? Which is essentially
Right.
inorganic.
So then you're saying that, but if you're putting the video over the visual, the organic, are you saying that that is the more fundamental, or that is what?
Well, it doesn't have the particular sense per se, you know, the actual sense, the organic sense. It doesn't have. So I will differentiate between inorganic sense and organic sense. Inorganic sense will be like positive and negative, like the charges. If you have charges, like I have positive charge, negative charge, or rotation, it can rotate clockwise, anti-clockwise, or left-handed, almost left-handed, right-handed, but it's not. It's still inorganic. But the left-handed, right-handed may be the connection because it become chiral, like with our carbon symmetry, you know, carbon things. Then it can become organic. So when it become organic, now the sense extends to our seeing, hearing, tasting, smelling, and touch, you know, feeling, touching, and all that, or
Okay.
feeling.
So you'd have to get into genetics then at that point.
Yeah.
Okay, fine.
So,
So did you find out about the definition of flavor? What was the
yeah. So I kind of briefly told that. Let me pull up that, and I have. I think I may be able to pull up that. Let me see. In the okay, let me see. I can pull up on the screen here. Try to change. Okay. I have to change it to 1 minute. I have to get it. Where is that? Where is the cursor here? Oh yeah.
Well, while you're looking for that, I suppose I should just say sort of the last sort of word on the Hermitian operator or transpose was that, yeah, that seems more like a group theory kind of thing, you know, where you have the identity, you have A and then the inverse or times the identity or whatever.
Uh-huh.
All right. Yeah. And then you get the, yeah, A inverse times A equals the identity. So yeah, that's more in the weeds, I think, of the whole, you know, group theory kind of thing. Well, the work I'm doing with the 600 cell and 120 cell is a bit more high level than that.
Okay.
So I don't need to worry about that because you know, when I'm reading this stuff online, I'm like, right, there's quite a bit I don't know, but then it turns out that I was overreacting. But it's still like there's still I still think there's more that we could do just to be more certain that we know what we're talking about. But
no, but can you see it now? Something?
oh yeah, there's something going on here.
Yeah.
Yes.
Maybe
I can see that.
Yeah. Okay, so there the flavor is there. You see.
Oh yeah, this is an interesting one. What is?
So let me go back.
I think I've been
so
to
this. Is a flavor.
Yeah.
The flavor. So it says that. So when I go down, the flavor thing, I found an interesting thing.
It's all about symmetry,
The
isn't
action
it?
of the weak force, describing mass and electric charge,
Yeah.
and this is not a flavor change. So the flavor probably includes both mass and charge in some sense.
Oh, okay. Yeah. Well, these are the symmetries, isn't it, of the
Yeah.
leptons and the quarks. It's pretty interesting. This is a whole SU2 thing where there's a symmetry breaking going on with the right and the left, and I don't fully understand that. So I'm going to try and change your well, I'll put a full screen maybe.
Okay.
Yeah, that's a bit better. So so yeah, you have chiral anomaly there. We don't need to get into that. But if you go down flavor symmetry, here we go.
The strong interactions conserve all flavors, something like that. And flavor symmetries.
Yes. Right. If there are two or more particles which have identical interactions, then they may be interchanged without affecting physics. So if we have, let's say, an electron and a muon, would they have identical interactions? All complex linear, or are we saying two electrons can be switched? All complex linear combinations of these two particles give the same physics as long as the combinations are orthogonal or perpendicular to each other. Okay. I'm not sure why. Is that because matrix again? Do you think?
Yeah, it has to do with the vectors, right? If the vectors are orthogonal, they are independent of each other, whereas the two vectors are are at an angle to each other. They can be resolved, and then so they are components of each other, right? If we resolve them, so like electric and magnetic field, they're orthogonal.
Yeah.
But that but only the interaction brings them. But if they are at an angle, then you can resolve them, and you get components of each other affecting the others. So that's the idea of orthogonal. Yeah.
Okay, you wouldn't get an electromagnetic or an electric and a magnetic field that aren't orthogonal to one another, though.
Yeah. So that's why the motion will be in the third direction, right? Always. So we have the cross product of the electric and magnetic field that gives the motion.
So that tells you what direction the particle is going to travel in when it's
yeah.
Oh, I've never seen that being done before. That'd be interesting.
I mean, that comes in the Maxwell thing, in a way, implies that. I don't know how much they are used, but I think more. I think that they should. We have to probably distill it down to that. And there is like what you call the what is that? What is that vector? What is that product? I was trying to remember that. They're like cross M, which E is the electric field and M is the magnetic field, is called is used a lot. I suddenly forget that, but that's a very important concept of understanding the electromagnetism. So because the the motion occurs in the direction perpendicular to both magnetic field and electric field. So that's the interesting aspect.
Okay, so continue on here then. In other words, the theory possesses symmetry transformations such as M, which I presume is what, mass or something, where U and D are the two fields representing the various generations of leptons and quarks, see below, and M, okay, M is any 2x2 unitary matrix with unit determinant. Each such matrix form a Lie group called SU2. See special unitary group. This is an example of flavor symmetry. So U and D are the two fields.
Yes.
Right. So one field could be a lepton, and another one could be a quark, or it could be maybe a muon or something.
Yeah.
Or like an electron, or electron and a muon or something. And so we have M is some unitary matrix, which is a part of SU2. But you could also get, oh, it's unitary. So it's not, yeah. Okay, so then you multiply that by the two fields, which, I mean, U and D look like up and down, don't they?
Well, the representing generations. Generation means division
I mean,
of
are they really when they're talking about SU2, they're talking about the gamma matrices, aren't they, at this point? Or are they?
Let's see, SU2 is the
you know how SU2 comes into like the Clifford algebra and the gamma matrices, and
they're not talking about that here.
Oh, you don't think so? Okay, fine. But they do that does come into like when you want to find out whether particles spin up or spin down. And that's why I'm thinking you've got M times a vector, which is U and D, and U and D.
Quark, yes. The U and D in the quark comes, right? The up and down.
Up and down quarks, but there could also be just spin up and spin down, right? So, because if you read the next sentence, it says leptons and quarks. So it's definitely not talking about just quarks.
Yeah.
And it's definitely not talking about the first generation of quarks, because it says various generations. So U and D cannot relate to up and down quarks. It must be up and down spins of the field.
Could be.
So that's what they're talking about. All of this here then seems to be just about what I just mentioned, which is the that algebra, you know,
the algebra,
the Clifford algebra, and the gamma matrices. I think that's all that is saying. So in quantum chromodynamics, flavor is a conserved global symmetry. That's interesting, isn't it? So well, I guess that makes sense because it has mass and the charge, like you said. In the electroweak theory, on the other hand, this symmetry is broken. So flavor is broken in the electroweak symmetry. Is that what they're saying?
Yeah.
Oh, and flavor changing processes exist. Okay, so yes, because we can have the what is it called? The CKM matrix.
Yeah.
Where you have quark decay and you know where
they combine. They can combine to form hadrons.
No, I think you're saying a quark, like a top quark, decays into a charm, and a charm decays into an up quark, and so on.
This one, okay, right here. Right.
And then we also have the neutrino oscillations. That's a very similar. I think there's a very similar matrix to the CKM matrix that's based on that. I've forgotten its name though. Okay, so continue down. Flavor quantum numbers. Leptons. All leptons carry a lepton number, L equal to 1. In addition, leptons carry weak isospin, which is -1/2 for the 3 charged leptons. So, okay, and +1/2 for the 3 associated neutrinos. Wonder how they figure this out. Each doublet of a charged lepton and a neutrino consisting of opposite T and weak isospin are said to constitute one generation of the leptons. Okay, so each doublet of a charged lepton, and so the doublet is a lepton and a neutrino consisting of opposite weak isospin constitute one generation of leptons. That makes sense, I guess. It's a weird way of saying it. In addition, one defines a quantum number called weak hypercharge, which is -1 for all left-handed leptons. Weak isospin and weak hypercharge are gauged in standard model. Okay, so they're gauged. What does that mean? I mean,
so they're removing.
If you're moving from one thing to the other, the value changes or something. But it doesn't change. It wouldn't change like in a. It would change in a very discrete way. It would either flip from like plus or minus. I don't know. Leptons may be assigned the 6 flavor quantum numbers, electron number, corresponding numbers for the neutrino. These are conserved in strong and electromagnetic interactions, but violated by weak interactions. Therefore, such flavor quantum numbers are not of great use. So that whole sentence there, or a couple of sentences, doesn't seem to have much impact. They're saying that it's not of great use. A separate quantum number for each generation is more useful. Okay, this is probably better. Electronic lepton number for electrons and electron neutrinos. Electronic lepton number and muonic lepton number and tauonic lepton number. They seem to be all the same, right?
Yeah.
Okay, and those are for tau leptons and tau neutrinos. However, even these numbers are not absolutely conserved, as neutrinos of different generations can mix, which is what we read earlier about the neutrino oscillation, I think. That is, a neutrino of one flavor can transform into another flavor. So they're not conserved, meaning if they were conserved, they wouldn't be able to change, right? They'd be the same always.
Yeah.
The strength of such mixings is specified by a matrix called, and there was the matrix that I couldn't remember the name of, PMNS matrix. The Ponto-Korda-Maki-Nagagawa-Sakata matrix, if you're ever going to remember that.
Oh, Nakagawa.
Nakagawa, yeah, that's a good name. Okay, and Sakata is a good name too. Okay, so yes, so basically what I'm getting from that is they have all these systems, but none of them are really, there seems to be no kind of bare essential reason for why these systems are the way they are. They just, this is how it is, and this is how it works. And you have, there's no, they're not saying, oh, because we have this PMNS matrix, and that means that we understand why that, you know, this is not conserved, but in the other case it is conserved. It's just a fact of reality that these two things are different. So what I'm saying,
a lot of it is mathematical, right?
There is that we don't have to, they don't know, so we don't have to worry about the fact that we don't know. If you get me. That's what I'm thinking.
A lot of it is mathematical, I think. It's not.
Well, I think it's also based on experiment, isn't it? A lot of these things.
Some of them, some of them are like standard model. They're there. Let's see, because they proved about the electroweak. Essentially, is proved, and the Higgs boson. So standard model, I think, is in that sense is proved.
Yeah.
Periodic table of the particles. So from there, they are deriving some of the things.
Okay, so we're getting some comments here from, which is interesting because we never got comments before on videos until maybe a week ago or two. So JChick 2020, he's saying, I believe they are all the same, just different scales from particle radiation emissions. So I'm not entirely sure what that was about. Now how they entangle to their geometric from hydrogen. Same thing, just opposite signs. I'm not sure when these comments were made recently, but numbers experiment is necessary to find that constant.
Oh, it's just 2020. I thought it's not the year they made it, right? It's just that.
Yeah, no. That's just their username. Numbers experiment is necessary. Oh, yes, we were talking about experiments. Yeah, that's necessary to find out. Yeah, that sounds right. So, okay, so that's pretty good. Is there anything else on that page that you're interested? I mean, we've got quarks here.
Anything? Quark, they carry quark or a baryon number.
Yeah.
Anti-quarks have negative baryon number. Weak
isosspin. Really their charge, isn't it? In a sense, here, same as their charge.
Uptight quark. So T3, the isospin is plus half. Negatively charged particle, down or strange or bottom half. Down type quarks or T3 is isospin is negative half.
Yeah.
So the charm, all of them top quarks. the strange and the bottom cogs, the down, they all have the same isospin.
Yeah.
Each doublet of up and down constitutes generation. Okay.
Yes. Each doublet.
So their flavor number, they are described by flavor number, quantum number, and the mass. Okay. Oh.
For all the
Okay. The quantum numbers, the convention is that flavor charge and the electric charge for quark have the same sign. Any flavor carried by meson has the same quarks. So you have to specify flavor charge. Do they specify flavor mass also? I don't know.
Yeah, that's funny because I would consider flavor to be more to do with mass.
More general. Mass and charge, it seems. The combined thing.
Yeah, but also they seem to be talking about generations as doublets. Did you notice that?
Yeah.
So that's kind of weird, isn't it? Because I wouldn't normally. Yeah. And you know what they're not getting into here is the fact that when you like it's SU2 cross, but it's like SU2 with us with for right-handed, and then that cross SU2 with left-handed.
Mm-hmm.
And then there's some weird thing that doesn't, like the symmetry breaks. Like if you, like they're non-commutative. So if you do it one way, you get one answer. You do it the other way, you get a different answer. And that's how the whole thing operates or something. But they should mention it on this page, but they don't. Yeah. They don't explain how it works. And I've looked pretty much everywhere on Wikipedia, and I can't find. They never explain the actual method. Although there should be a table that shows it. It's probably something very simple. That's the CKM matrix I was talking about.
The flavor problem. Flavor puzzle is the inability of current standard model to explain why free parameters of particles have the values they have, and when they have specified values for mixing angles, PMNS, and the CKM matrices, the fermion masses and their mixing angles.
Oh yeah.
It will be specifically tuned. And the reason for such tuning would be the solution to flavor puzzle. There are fundamental questions involved in puzzles, such as why there are 3 generations of quarks. Down, charm, strange, and top. And leptons, electron muon, as well as how and why the mass and mixing hierarchy arises among different flavors.
So there's really quite a lot they don't know, and a lot of this points to stuff outside of the standard model they're thinking.
Yeah.
Whereas what it seems to me, you know, based on the research that I presented, was it last week on leptogenesis?
Yeah.
How there's these 8 new particles, and there's a 6-2 split, just like with the gluons. That there could so because the gluons are connected with the color charges of the quarks, and the quarks are you know involved in the flavor thing, obviously, with the different generations, and that could lead to the generation of the quarks through the leptogenesis side of things as well. Then could be, which would lead to baryogenesis ultimately, right? If the quarks make up the baryons, then so my thinking is that the symmetry of these 8 leptogenesis particles are what's making the other symmetries that we see. So that could be you know, it is physics outside.
Is a conjugate, like a conjugate symmetry?
It wouldn't. It seems to be basically the same thing repeated. Like, So there's strange things going on there. There it is. SU. So special unitary with sub L times SU sub or. Yeah.
So that's approximate flavor symmetry. Approximate.
Well, it says chiral symmetry description. So this is getting into the chiral part, maybe. Under some circumstances, for instance, when the quark masses are much smaller than the chiral symmetry breaking of 250 MeV. Wait, Rajan, go up. I can't read it. Keep going, back up. Yeah, thanks.
Right here, right?
Yes, yes. Under some circumstances, for instance, when the quark masses are much smaller than the chiral symmetry breaking scale of 250 MeV. So that's interesting. The quark masses are usually a lot smaller, are they? Yeah, they're about 4.7 GeV, is it? All right, we'll have to look into that, but no, maybe it's 4.7 MeV for like the top quark or the up quark or down quark. I mean,
down quark is heavier.
Yeah, you're right. So the up quark is about 2.2 MeV, I think. Right. So the masses of the quark, and so the chiral symmetry breaking scale. So that's like a temperature where you go back to the beginning of the universe, and would imply that above that temperature there is no chirality, right? Everything is right and left don't exist, I think is what they're saying. The masses of quarks do not substantially contribute to the system's behavior. And to the 0th approximation, the masses of the lightest quarks can be ignored for most purposes. Okay, that makes sense because of, as if they had zero mass. Oh, and I was thinking about how the electron and the neutrino, some people consider them to be massless because they're basically just rounding errors. But we'll see. The simplified behavior of flavor transformations can then be successfully modeled as acting independently on the left and right-hand parts of each quark field. Okay, simplified behavior of flavor transformations. See, that's, you read that sentence and you think, okay, I understand, but there's quite a lot in that.
Yeah.
So anyway, if we go on, this approximate description of the flavor symmetry is described by a chiral group. And that I can't find any info on that chiral group. And I'm assuming that when you have this cross thing that they're saying one is, there's a non-commutative element there, but maybe not. Maybe I've just made that up in my head.
So left and the right, right?
Yeah. So what is a left-handed special unitary matrix? Because I've never seen one, I don't think. I know I can find left-handed and right-handed matrices in SL2C, and even though you're not meant to, but you can do it, I think. But I've never seen the same thing with SU. Okay, well, let's say it's SU2, right? Because they don't even put in the number there. Maybe N could be 2. So sub F, I don't know what F means. That's the field, is it?
Yeah.
That would be like an electron.
I think so.
Okay, yeah. So it's like back to what we were talking about earlier, where we had M times U and D as a vector.
Yeah.
So we have this matrix M or whatever, and so that's going to be an SU2 matrix, right? Now we know that in the SU2 group there's the identity, which we're not interested in. Then the other 3 are 3 rotations which can conform to the quaternions. So we might think of them in that sense because it would be easier. And then one is rotating around the XY axis, another one the YZ axis, and the third one the XZ axis, let's say. So those are our 3 rotations. Maybe one of those rotations, like the XZ or something, could be spin up and spin down rotations, and the other 2 then could form left and right. So then we're really just saying that we're multiplying one specific. But the thing is, if you multiply, let's say we're saying I is for spin up and spin down, like plus or minus I, and J and K are left and right, then if we multiply J by K, which is what they're doing there, I think, then we get, well, it's a cross product or something. But if we do multiply them, we're just going to get I, which will give us a spin up vector, which is not what we want. But if we do it the other way around, we'll get minus I, which is a spin down, which is also not what we want. So see where I'm struggling to follow what we're talking about? Just
it's not very clear. They should give examples too.
Yeah, there is a pretty cool table, maybe on this page or some related page, that kind of makes you feel like you know what you're talking about when you're reading it. But I'm not sure if it's it is on a related page. I'm not sure which one though. But basically, it just shows it basically shows what we already know, that there's like right-handed particles and left-handed particles, but it makes you feel like you know what they're talking about. But I'm not entirely I'd like to see the mathematics, like, because it's only 2 by 2 matrices. How difficult would it be to write it out, you know? But I can't find it anywhere. Okay, so there's more comments here that might help. Yes, angles start from 1, and the bond angle, I don't know what bond angle. Magnetospheric toroidal black hole particles can keep stacking until max density charge that leads to collapse. Okay, so, well, okay, so the ratio in volume to the micro levels. Okay, so there is what's the name of that? Flavor _ particle physics. So yeah, now there's a Wikipedia page on flavor symmetry.
Oh, you want me to get off here?
No, you're fine. I'm just because I already looked up that page before and I found it very interesting, but I kind of got to a point where I couldn't go any further with it. So it looks like I looked at that back in September, some stage. Oh, and also in May. No, September. Actually, September 11th, which is really only, how many years is it since? It's 23 years. Right. Okay, so, oh yeah, here we go. There's chiral symmetry breaking, spontaneous symmetry breaking, chiral anomaly, weak isospin, and space group. So I think probably it'll be in flavor particle. No, that's what you were in. So I think it's in flavor symmetry. Paste. Oh, what's it? Yeah, okay. This is the first one. I don't know. Yeah, this is the same thing you're in. There is one thing. There's another part here where it's talking about, in the section on quarks, it talks about special mixture of quark flavors is an eigenstate. Okay, the weak interaction part of the Hamiltonian. I think that's a little bit. It might be a little bit complex. There's chiral symmetry breaking at the scale of 250 MeV. We're talking about that. If you go into that, we have quantum chromodynamics. Massless fermions in 4 dimensions are described by either left or right-handed spinners that each have 2 complex components. These have spin either aligned right-handed chirality or counter-aligned left-handed chirality with their momenta. Okay, so Yeah, there's the spinners. So the spinners do have left and right associated with them. But you see, I thought it was SL2C that is supposed to break into left and right, but I don't think it does actually. I think that's the problem, that they weren't able, there's no way of making it, or there's, when you just have SL2C, there's no right or left. But I actually found, if you look at the S8 matrices for SL2C, you can break those down into right and left. So maybe that'll be useful for them. But they use that in kind of with the Lorentz group and that kind of side of things. So it's more like the general relativity quantum field theory part rather than the quantum part. Whereas we're looking at the quantum part here. In this case, the chirality is a conserved quantum number of the given fermion on the left and right. Well, it says it's conserved, right? But when a particle moves through space-time, it can change its can change being right-handed or left-handed, can't it? But
can it change the chirality?
Well, yeah, there's two different things though, isn't there? There's helicity and then there's chirality.
Yes.
And helicity is like the projection of the spin, the chirality spin, I think, in the direction of travel or something like that.
Oh.
So, but I could be getting mixed up. It could be, no, I think that is helicity. So chirality then is just whether it's right or left-handed, I think, which is a conserved, it is conserved in a sense that no matter which direction you look at the particle from, it will always look right-handed or left-handed. But yeah, because that's what the weak that experiment that was done into beta decay with the matter or antimatter particles, or it wasn't actually matter or antimatter. I think it was the chirality issue. They found that so if you wanted to talk to an alien and you wanted to explain what you meant by right-handed or left-handed, you'd show them that experiment and they'd always know what direction you were talking about.
Wow.
In this case, the chirality is a conserved quantum number of the given fermion. So that's a bit odd. It's a bit of an odd statement. If previously we saw that a conserved number wasn't conserved if it could change. For example, it's the neutrino mass oscillation. And here we know that chirality does change as a particle moves through space-time. So that should seem to be not a conserved number either. But let's just ignore that for the moment. And the left and right-handed spinners can be independently phase transformed. Okay, so seems to say that they can be transformed into one another. Oh no, phase transformed. I mean, a phase is a different part of the wave, isn't it?
Yeah.
And it doesn't really affect anything. Like you can mess around with the phase all you want in lots of different quantum mechanical equations, and it has no real effect on the result. More generally, they can form multiplets under some symmetry group, GL times GR. And so that's, I don't know what that means, but it looks like we're back to the SU2 L times SU2 or thing. But again, it's not very clear, is it? A Dirac mass term explicitly breaks the chiral symmetry. Okay. In quantum electrodynamics, the electron mass unites left and right-handed spinners, forming a four-component Dirac spinner. In the absence of mass in quantum loops, QED would have U1 sub L cross U1 sub OR chiral symmetry, but the Dirac mass for the electron breaks into a single U1 symmetry that allows for a common phase rotation of left and right together. Okay. Single. which is the gauge symmetry of electrodynamics. Yes, that's true. At the quantum loop level, the chiral symmetry is broken even for massless electrons. There's massless electrons by the chiral anomaly, but the U1 gauge symmetry is preserved, which is essential for consistency of quantum electrodynamics. Well, there's an interesting thing here. I wonder, like, is that section that I just read out, that paragraph to do with the Dirac mass term breaking chiral symmetry, is that basically the maths that we're looking for, where we're talking about SU sub L cross SU sub OR?
Oh, is it?
It could be, couldn't it? Because it sounds like that might be useful in that. The electron mass unites right and left-handed spinners. So that all they're saying there is that you have a right-handed spinner and a left-handed spinner, and they both have the same mass.
Oh.
So I would say that that's, well, no, I guess mass is not really conserved. But this forms a 4-component Dirac spinner, I guess. I think that's what they mean anyway. In the absence of mass and quantum loops. Now, why would they say in the absence of mass? Because we're talking about massless electrons, and I've never heard of those before. Have you? Okay. Yeah. But the Dirac mass of the electron breaks this into a single U1 symmetry. So the mass breaks it into a single breaks. Wait a second. But the Dirac, all right. So what is a Dirac mass?
Wow, Dirac mass.
Yeah,
I never heard about that.
Yeah, because there's loads of different types of mass. Okay, rest mass and I guess, you know, but Dirac mass. You know, what's the deal with the Dirac equation? It basically takes the normal Lagrangian or Hamiltonian of quantum mechanics, sorry, and brings it to higher energies, is it? So when we're talking about getting closer to the speed of light, so maybe when they're talking about Dirac mass, they mean relativistic mass?
Yeah, probably it is.
Okay.
That makes sense.
Right.
I don't know what it is.
I still don't know why they're talking about massless electrons, but in the absence of mass, so in the absence of Dirac mass, meaning in the absence of speed, right? Relativistic mass. And quantum loops. So no loop diagrams, no perturbative mass added into the equation. Quantum electrodynamics would have a U1L. So basically a circle spinning one direction times a circle spinning the opposite direction. Chiral symmetry, which sounds like nothing, right? Because yeah, plus and minus equals 0. But the Dirac mass, so they're saying in the absence of mass, you'd have this, but the Dirac mass is there. So how is that the absence of mass of the electron breaks this into a single U1 symmetry? So that allows for a common phase of rotation of left and right together. So that's weird, isn't it? Because it says a single SU1, or sorry, a single U1 symmetry should only be left or right, yeah? But it's saying that there's a now left and right together. So none of that is clear. I don't think either the person who wrote that doesn't know what they're talking about, and they haven't given any references. So, or they haven't been very clear. They haven't explained themselves very well, or else they're using terminology that's just outside of the normal scope of what I'm aware of. But yeah, we can see it here again. This is the primary consequence of the phenomenon of spontaneous symmetry breaking, of chiral symmetry in strong interactions. In QCD, the fundamental fermion sector consists of 3 flavors of light mass quarks, UD and S, as well as 3 flavors of heavy quarks, charm, quark, bottom and top quark. if we assume the light quarks are ideally massless, so that's probably what they're saying up here about when we were talking about massless electrons. It's just like they're considering them to be ideally massless because of the rounding error point that we made earlier.
Mm-hmm.
Maybe that's it. So they're just ignoring the mass, basically.
Mm.
Yeah, if we assume the light quarks are and ignore electromagnetic and weak interactions, so just forget about all of that stuff. We don't need it. Then the theory has an exact global SU3 sub L times SU3 sub OR chiral flavor symmetry. So SU3 are those Gell-Mann rotations, right?
Yeah.
For the gluons.
The gluons, yeah.
Yeah, but they also appear in QCD, which is quantum chromodynamics, which is, well, it's about the color charge, isn't it? Which, to be fair, the gluons mediate the color charge, so that's okay. So this is what I'm talking about, you know, the leptogenesis particles. There's 8 of those. And
okay.
Yeah, although actually, but we see that there's this SU3 sub L, so it's chiral, and SU3 sub OR. So it does seem to go back to, right, so it seems to be dealing with color, charge, so charge, like you said, and chirality. And then, but then they're saying chiral flavor symmetry. So flavor, we noted, was to do with the different masses like U, D, and S, or, you know, remember we said the 3 generations?
I see. Okay.
So yeah, so that's why I'm thinking that we might be able to draw a relationship between the leptogenesis particles and the gluons, and therefore into different aspects to do with, you know, the charges, maybe even the flavors. Although it's getting a little bit confusing.
Yeah.
I don't really know what an SU3 sub L matrix is, because, I mean, what do they do? Like if you use an SU3 matrix, it can rotate a cube, you know? Okay, so maybe it rotates it in one. It can rotate the cube, let's say, in the XY plane. Probably doesn't do that, but let's just imagine it does. And then it can also rotate it in the minus XY plane. So that presumably would be right and left handed. Okay. But then wouldn't that imply that they're, so there's 8 matrices in SU3. So half of them must be right-handed and half of them must be left-handed, I guess. So that would mean 4 for each. Does that really help in any way to better understand?
I don't know. So SU3 you are breaking up into left and right. Is that right?
Yeah. Oh yeah, you can't see this, can you?
No, I cannot.
Oh, maybe I should share this, should I?
Yeah.
Okay, I'm going to present share screen.
Should I get off?
I think it'll just
automatically. Okay.
Yeah, I think it will
automatically switch. Okay.
Okay. What else do we have? All right, I'll come back. So you can read out those comments in a little bit if you want. Right. This one, can you see this?
Yeah. Let me. Let me make my screen full. Okay.
Righto. So this.
Thanks.
So this is what I'm talking about here.
Oh, SU3L and SU3R.
Yeah. So, So yeah, beyond the idealization of massless quarks, Well, hang on. Is this okay? Under spontaneous symmetry breaking, the chiral symmetry is spontaneously broken to the diagonal flavor SU3 subgroup, generating low mass Nambu Goldstone bosons, which are just
they are not gauge bosons, right?
they are, aren't they? They're just like
They
they just U1, aren't they? They just go around in a circle. Okay, these are identified with the pseudo-scalar mesons seen in the spectrum, and form an octet representation of the diagonal SU3 flavor group. Pseudo-scalar, that's a term that comes up a lot. I've forgotten what it refers to, though.
Pseudo-scalar means it could be partly vectorial.
Yeah, maybe
in the vector space. They are still in the vector space. They are not in the real space.
Maybe, yeah. Could be something like that. Or maybe it's something that behaves like a scalar but isn't.
They're just vector fields, but they behave like scalar.
Yeah, maybe there's some like, there's some cross product involved or dot product, I mean. In the span, right. And then we're just back to the octet representation of SU3 flavor group, which we just left. So now that, I just don't think this is very well written or very useful. But I'd say someone who knows a lot on this subject would probably read that and go, yeah, I understand that. I don't understand that. Beyond the idealization of massless quarks, the actual...
I like to simplify things.
No, for sure. Okay, so I'm looking for... Oh, yeah, here we get into it more. You see, so they're talking about it a lot, like quarks and mass generation. Oh, yeah, and the mass gap is a big thing that I've...
Well, that's a Yang-Mills thing, right? Kind of mass gap.
Yeah, maybe. Yes, I think you're right. Yeah, because they're looking for an answer to that, aren't they?
Yeah.
Okay. Light quarks and mass generation. If the 3 light quark masses of QCD are set to 0, we then have a Lagrangian with a symmetry group. Well, why would that be the case? Okay, and this is the symmetry group here. U1 sub V times U1 A sub A. I don't know what they are.
Oh, so two different
symmetry groups. Or, well, this is, yeah.
This is your, the field.
Maybe it's to do with the Lagrangian, is it? V is like a vector, or not a vector, but a charge or something. U plus V equals T. It's the potential, but no.
It's connected with the gauge.
Probably. Okay, note these SU3 symmetries called flavor chiral symmetries, right? Should not be confused with the quark color symmetry, SU3 sub C. So that's hugely confusing, isn't it?
Yeah.
Like how many times
you put the thing on symmetry group, you put the what you call the your browser. Does it
you
say
can see it now in the group? Yeah. In group theory, the symmetry group of a geometric object is the group of all transformations under which the object is invariant. We kind of know this, don't we? And with the group operation of composition, such a transformation. So we kind of know that, but that's what we're
but they're not talking about what UNV and UNA is about.
Yeah, no, they didn't mention that. VA. Oh, that might be like up and down or vertical. And
is it under that? If you click,
no, there's no links.
Is it in that?
Oh, if I go down, you mean? No, I don't see any. Oh, they mention it here again. V divided by V. So technically this...
The coset space. Look at the coset.
Where does it say coset?
Yeah, the coset. Press that. Technically the spontaneous, just before that. Just before the left of that.
Oh yeah. Comprise
the coset
space.
So press on the coset. Can you press on the coset?
Yeah. Mathematics, specifically group theory, a subgroup H of group G may be used to decompose the underlying set of G into disjoint equal-sized subsets called cosets. Okay, so a subgroup may be used to decompose, right? Okay. Yeah, I think we see that. We see that quite a bit. So the cosets in this case are the left and right cosets.
So if you press on that...
so this is a coset, and that's a coset, and then it's divided maybe by the entire group. So if we're looking up... Oh, wait a second here. Vector subgroup. That's what it stands for. The V is vector.
Oh, diagonal vector subgroup.
Yeah.
Okay.
I don't know what the
other one is anti-diagonal, probably.
Yeah, probably. Yes, yeah, which would just be 0, wouldn't it? For U1 matrix. Okay, but does the vector describe the diagonal? Doesn't really, does it? And what's a vector? What's a vector subgroup of
diagonal vector subgroup?
So they're just looking at the diagonal of the matrix.
Yeah.
Which is just a vector full of 1s, and this is a vector full of 0s.
It's like kernel type thing.
Oh, yeah. That's very maths heavy. Right. Right, so they shouldn't be confused with the color symmetry. So that really worried me when I saw that, because, you know, we're dealing with QCD, which is color symmetry, isn't it? Chromodynamic?
Yeah.
And then they're saying it's not to do with color symmetry. That defines... Oh, we'll read on. That defines QCD as a Yang-Mills gauge theory and leads to the gluonic force that binds quarks into baryons and mesons. So, right. So there's the SU3 color symmetry, and then there's this other SU3, which is a flavor chiral symmetry.
That's really twisting, tongue twisting.
Yeah, it's so this one I think is to do with mass, right? And this one is to do with the gluonic force, which also contributes to the mass, doesn't it, of the baryons?
They're more what you call they're like.
So I'd say a good deal of the mass might come from this.
Oh, the gluons, they're not. Are they just mediators?
But yes, and they're massless mediators as well. But they generate either this. I don't think the color symmetry generates mass, does it? But this might. One of them definitely does. Or maybe both. In which case, they're
both charge and mass. They create charge and mass, huh?
Yeah, I mean, a color doesn't is a charge, so it shouldn't have anything to do with the mass, right? Technically.
Yeah.
Okay, so then we can. That's what we're going to say. That this is the mass. This one is the mass. And that makes sense maybe because it's got this L and OR. So it would have a right and a left, which would then have something to do with this. Doesn't Yang-Mills theory have something to do with the Higgs field, which only binds to like left and right particles?
Yang-Mills is a stronger thing, right? Higgs is more weaker. Is it true?
I thought Yang-Mills was only a very like I'm surprised that people go on about it so much. Maybe I'm confusing it with something else, or definitely a yang. It's yang is involved, and it's like, oh, you mean strong or weak forces? Is it?
Yeah.
Yang males is a weak thing,
Is it?
isn't it?
Doesn't come in the strong. The Gelman thing, the yang males doesn't come.
Oh, that's a good question. Is yang males not used in like lots of things? But I read about it, and it seems like it wasn't as, what's the word? It was like just a solution that only works in a very small area, and wasn't a general solution to
Oh, it's
things.
just a unification of electromagnetic and weak forces.
Well, that's a huge
As well
deal,
as
though,
quantum chromodynamics. So it try to connect the theory of strong force as well.
as well. Yeah. See, but so that sounds like that's a huge deal.
That's what I thought. Yeah.
Yeah, and people are talking about this all the time. Is like really important. But when I was reading about it in a book recently, now maybe I'm confusing it with a different one, but it was like this is they were basically saying that it wasn't actually finished, or that it didn't work in all cases or something.
They're
So
trying to unify, right? They're trying to unify the weak, the strong, and the electromagnetic.
oh yeah, well, let's go back and read it. Is a quantum field theory for nuclear binding devised by Chen-Ning Yang and Robert Mills in 1953, as well as a generic term for the class of similar theories. Oh, great, great. Yang-Mills theory is a gauge theory based on special unitary group SUN, more generally any compact Lie group. Yang-Mills theory seeks to describe the behavior of elementary particles using non-abelian Lie groups, and is at the core of the unification of the electromagnetic force U1 times SU2, as well as electron. Thus, it forms right. So the question is, which part of what we were reading is this? Is it all of it? Is it like everything with an SU L sub L and SU sub or was it all of the other ones that didn't have the? Presumably, it has a lot to do with chiral symmetry, does it?
The Lie group, yeah.
Right, and it. Okay. Covariant derivatives, coupling constants.
I don't know. It's just a mathematical manipulation or not. Yang-Mills thing,
What do you mean? Oh, a bit like, yeah, because there's a lot of stuff like that with the Gelman stuff. It's like, it seems a bit odd.
So you're kind of forcing the math into the physics, kind of thing.
Right. I mean, you'd probably be more able to. Yeah, sometimes I feel that, like where we were talking about the the Clifford algebra, where you have this matrix and then you multiply it by the up and the down to get, and it just seems so like, well, you could have just written like, I have an up particle, instead of bothering with the matrices. But yeah, there must be something more to it that I'm not seeing. Obviously, you can start adding them into like much more complicated equations, and then you can start getting answers out of them in a more general way. But yeah, instead of just putting them in by hand, something like that might be the reason. These rules for Feynman's diagrams can be attained by the generating functional given above. Oh, can be obtained when the generating functional given above is rewritten as blah blah blah. This is very all right. So we get into the ultraviolet thing again. Lattice. That's not what we want. Okay, so we go back here. Where did we leave off? We were down here a bit. Oh, okay, so
there, yeah.
yeah. So I was wrong. So this part had nothing to do with the left and the right. I don't think. So
it's not chiral thing. Yeah.
It's not chiral.
Yeah.
So much.
Young Mills, I don't think talks about chirality.
But it is talking about merging like electromagnetism with the weak force, right?
Yeah, yeah.
And that's got chirality in it. So maybe it's got chirality on the weak side, but not for the quantum chromodynamic side.
Yeah, yeah.
Okay, that's so confusing, isn't it?
Yeah.
I mean, yeah.
Is there a chirality in the strong force?
Yes. Look, would you like you wouldn't expect it, would you? Note that right. Okay. In this article, we will not focus on the binding dynamics of QCD, where quarks are confined within. Right, we know that. A static vacuum condensate can form composed of bilinear operators involving the quantum fields of the quarks in the QCD vacuum known as a fermion condensate. I think you've talked a lot about that. It's driven by quantum loop effects of quarks and gluons. And it has to be less than this because this is the symmetry breaking temperature, right? Chiral symmetry breaking.
Oh.
The
mass aspect, right? Is that mass?
No, it's a temperature. Above this energy scale, right and left doesn't exist.
Yeah.
It has to be below that.
It's kind of like a Curie temperature, but for this one.
Right, yes. And a static vacuum condensate can form under this temperature, right, known as a fermion condensate. So condensate sounds like something that's kind of cool, doesn't it? So is that a static vacuum condensate? So maybe they all have like one rotation or something then. Condensate will not invariant, is not invariant under independent rotations, but is invariant under common SU3 rotations. So that's kind of what we were saying, was it? Something about... Yeah, you see, that's weird. Is this common SU3 rotations referring back to this quark color symmetry? Whereas the independent SU3 SU3OR rotations are these, and that's weird, isn't it? Because shouldn't this like if this SU3 can be decomposed into our two cosets, then this has the two cosets in it already.
It's a combined one, right? It's combined one. That one is the differentiable.
Yeah. So you'd only be looking at the L or the OR in this one.
Yeah.
And so when you apply this coset to one of the quarks, maybe it's not invariant.
So it will produce different
results. If you apply it under this one, it is invariant. Okay, so this is a symmetry breaking under something like that. Pion decay constant F sub pi approximately equals 93 MeV. I don't know what that is. Pion decay constant. So that is basically where pions generally decay at. That energy level. Wait a second.
The symmetry breaking, it explains why the left exists and the right doesn't exist, or something like that.
Sorry?
The right-handed thing, in one of the things, the left-handed thing exists and the right-handed thing doesn't exist, or vice versa, right? In the asymmetry, in the symmetry breaking, the baryon asymmetry.
For the condensate?
Yeah. Matter asymmetry. The matter and the matter asymmetry. You have the left or the right. One of them is not there.
Oh yeah. Well, for the weak force, this is the strong force.
Okay. The strong force also has this, right? Left and right, but they don't have asymmetry.
Yeah. Well, maybe. I mean, quarks have electroweak symmetry, do they? Wait a second. They must do because they interact with W bosons. They also have the strong color symmetry.
Yeah.
And then they have this chiral strong symmetry, which presumably creates the mass. That's what we were thinking, wasn't it?
Yeah.
I don't know. The pion decay constant. In particle physics, the pion decay constant is the
You have to go through it a few times to really get real understanding.
Yes. I feel like we're
little,
we know a
each
bit,
time we get a little understanding, little more understanding, I think.
Exactly. We keep going over it until we get it. Quark condensate is induced by non-perturbative strong interactions and spontaneously breaks the SU3L times SU3 or down to the diagonal vector subgroup SU3V. Okay, so that's something we could look up maybe. Diagonal vector subgroup.
Yeah.
This contains as a subgroup SU2. So that's really interesting that SU2 should be a subgroup of SU3. So I've never heard of that before. Because SU2 is 2x2 matrix, and this is 3x3.
Yeah, you can get. I think I did some operation right and earlier where you can get SU2 from SU3, but it's not a simple thing.
That's a big deal, though, isn't it, to get that?
Yeah, yeah.
I thought so. The original symmetry of nuclear physics called isospin. Now, SU2 is now somehow also isospin. I didn't know that. Did you?
Oh, is it isospin? SU3?
SU2 is isospin.
Yeah, I thought
it's a symmetry of nuclear physics called isospin.
Yeah.
Well, that makes sense actually, because we were just through all that. This is kind of what we're trying to find out actually. So we might look at that.
I'll be back in like 5 minutes.
Okay, no problem.
Thanks.
Is it here? Okay. So this contains the subgroup SU2, the original symmetry of nuclear physics called isospin, which acts upon the up and down quarks. Yes, we know that. The unbroken subgroup of SU3 constitutes the original pre-quark idea of Gell-Mann and Neumann, known as the Eightfold Way, which was the original successful classification scheme of the elementary particles, including strangeness. Okay, just the original. Yes, and right, the U1A symmetry is anomalous. Maybe A stands for anomalous then. Broken by gluon effects known as instatons and the right. So this is all very, I think this is probably fairly theoretical. Did we find out what this meant? The pion decay constant is the square root of the coefficient in front of the kinetic term for the pion, the low energy dimensional energy scale. I think it's just the energy that they decay at usually. I don't know. All right, let's go back to here. I'm going to stop presenting. Now, what are we? Well, let's read some of the comments that we have. Right, sorry, a little scattered, but the pattern from hydrogen and on forth geometrically in bond angle. How they carry out with the stacking principle. Okay. So this looks like it's to do with black holes and all of that. Changed. Where's mass? I should probably share this actually. And share. Yeah. Okay. So gyroscopic effect for that massless effect. Not massless. Oh yes, this was back to when we were talking about mass, whether it was the Dirac mass or not. Resonant field forces. Yeah, I've heard that term a lot, but I'm not entirely sure. Well, resonant. I'll have to look that up. It's a good one. Scalar intermittence. So that was to do with the pseudoscalar. And I've heard of that term as well, scalar intermittent, but it's not very descriptive. All right, two will spin opposingly together around as concentric orbital where the neutron is their static charge medium. Yes. Okay, electric flux, electron, magnetic flux, proton rotation. Okay, rotation creates the static of the two. Pressure, mass could also be charge force. Oh yeah, because we were talking about charge being different to mass. Yeah. Defined by the rate with variable spin. It's very okay. Yes, I know. Okay, thanks. They were interesting comments. So we might look up that term, resonant field forces, in a bit. There's also some other terms that I was trying to look up. Let's close those. And right, we'll go back to the articles. Oh, what did I do there? Oh yeah. Yes. Share screen. Okay. Oh yeah. Right. Right. Where did we leave off then? I'm not sure if we need to read too much more of this, actually. It's conformal anomaly. Which goes into Weyl anomalies for the light. Then there's Nanbu-Goldstone bosons. We mentioned them earlier. Technically, the spontaneously broken chiral symmetry generators comprise the coset space. The space is not a group and consists of the 8 axial generators corresponding to the 8 light pseudoscalar mesons. Okay. Non-diagonal part of this. So that goes back to, surely that's back to this guy's work. The pre-quark idea of Gell-Mann, the eightfold way. Is that not correct? They're all mesons. Subatomic particles known as hadrons. Mesons are hadrons. And this pseudoscalar mesons, they look the same, pions and kaons. So maybe pseudoscalar in the sense that we have the strange number, it could be +1, 0, or -1. They're scalar values associated with the kaon and the pion, but we wouldn't actually call a kaon and a pion a scalar. So that might be why it's pseudoscalar. Space is not a group. So it seems like this, according to this, this coset space are the 8 axial generators, which are part of the pre-quark idea of Gell-Mann. So this is all pre-quark stuff. This is later with the color charge. This has the quarks involved and the gluonic forces. So we would imagine that this is kind of more important, more fundamental.
I'm back.
Hey, you're back.
Okay.
So we had a couple of interesting maybe realizations here. If you look here, it says, where did it go? The original pre-quark idea of Gell-Mann and Niemann, known as the eightfold way, which has the kaons and the pions and all of those hadrons. And then if we go down here, it says spontaneously broken symmetry generators comprise the coset space. This space is not a group. It consists of the 8 axial generators corresponding to the 8 light pseudo-scalar mesons, which are again the pions and the kaons. We notice that they sit on these axes that are denoted S1, S0, S equals -1. So those are the strange numbers associated with the particles. So I was thinking, well, maybe that's the scalar, the pseudo-scalar. That's because they aren't scalar particles. Like, and so that may be an explanation for that. The non-diagonal part of this. So it seems like this is to do with the pre-quark. This coset space is a pre-quark idea of Gell-Mann. And so this then, the quark color symmetry is quantum chromodynamics, and this has gluons and it has quarks. So I'm saying that this is probably more important than this. Although, oh look, it says it right here, light quarks and mass generation, right? So we're talking about light quarks. So they are talking about quarks. So it can't be pre-quark, can it? And it says at the very beginning, 3 light quark masses are set to 0. So they want to generate the masses out of this method. They first set the masses to 0 to do it. That makes sense, I guess, right? That's what they're talking about. Mass generation. And we did say that one of these symmetries is to do with mass generation and the other one is to do with the color symmetry. So that would seem to be the case. Although I have to say this is pretty badly written if that's what they're trying to get at. Chiral symmetry breaking is apparently now here we go. So this is the point they're making. Is apparent in the mass generation of nucleons. So the generation of mass in the nucleons is made from the chiral symmetry breaking, I think. Since no degenerate parity partners of the gluon appear. Okay, so there's none of these parity partners exist, so that causes the chiral symmetry breaking, which results in the mass generation of the nucleons. Chiral symmetry breaking and the quantum conformal anomaly account for approximately 99% of the mass of a proton or a neutron. And these effects thus account for most of the mass of all visible matter. For example, the proton of mass P, right, is 938 MeV, consists of 2 quarks. Right, yeah, so we know this, don't we? It's just funny how we get to that from all of this. Seems to just jump in out of nowhere, kind of. Well, it is interesting. So we said we'd look up diagonal vector groups, subgroups. I believe that's what we're interested in. Showing that the diagonal is a subgroup. Diagonal subgroup. Very, very short article. Newton.ac.uk. Is that a university? St. Andrews.
St. Andrews, UK.
Yeah, that's a big.
Near where you are?
Huh?
Is it near where you are? No.
No, it's just the URL is newton.ac.uk. So I was wondering, is
no, the other side, huh? You are on the north side, right?
No, I'm in Northern Ireland, like the north of Ireland. But St. Andrews would be what, in the UK, probably in England, I imagine. It's not Scotland.
England is south of you, right? Is it south or southwest? East, southwest.
What? England?
Yeah.
Oh yeah, well, I would consider it kind of east.
East.
Yeah, but right now, yeah, actually, it's southeast. Okay, so diagonal groups. Oh, wait a second. Maybe we shouldn't launch into reading this entire paper.
Yeah.
Like
when you read, you can zoom in. If you can zoom in.
Yeah.
I mean, important once you get into important.
Yeah, that's a good question. I'm going to hide that. Go back to that. So this is very much theorem based. Let T be a which
theorem proof.
Yeah, proofs and lemmas and all of that. And I generally don't tend. You need to kind of sit down and work those out.
Yeah, it's more pure. This thing I like more applied mathematical physics.
Yeah, I'd agree. Folded. Oh, here we go. Diagonal groups and the structures they preserve have occurred in other places. Right, I actually don't think this is going to be hugely helpful. I think this might be a bit too far ahead. We just wanted. Let's ask Stack Exchange here. Having some trouble with this problem, let G be some group and let H subset of G cross G where H equals, what is this? G for G in G?
Element of G?
Yes. Where G is an element.
G is an element of G.
Yeah, and this is just, what, a coordinate? No, could be. This is sometimes called the diagonal. Oh, right. This is the diagonal, I think.
Diagonal.
Yeah. Subgroup. So this is a vector, is it? I guess.
Could be, yeah.
Could be.
It's like X and Y, you know.
Yeah. So that's kind of a vector. It's also a coordinate, though. Is a vector? Vectors and coordinates are different, though. So.
Yeah, I mean, they derive out of. Actually, a coordinate should be a vector.
Yeah, I see what you mean. It should be, shouldn't it, actually? Because you could have like vertical and horizontal. Yeah, and they're both the same. So coordinate and vector. Yeah, good point. This is sometimes called the diagonal subgroup of G cross G. Show that H is a subgroup of G cross G. So show that the diagonal is a subgroup of this other main group or something. This is because all elements of G cross G can be written as GG, and that is the definition of H. Any help would be great. Usually find these short comments not too useful.
Yeah, not useful.
Yeah, sometimes they can be good, but very rarely. Okay. It is taken that G cross G is a group. Since H, yeah, we know that. We define H, yeah, okay. These are two coordinate values in H. And then we say, where did A come from? And B. Just fucking jump out of nowhere. That's great. Okay, so what's this called? Where they're associative, yeah? A, B, A, B. We show H meets the definition of a group. associativity comes from G cross G. E is the identity element, since, yeah, similarly, yeah, for A, B equals C, where A, B, C in G, then AA, yeah, shows closure. So it's they're trying to prove it's a group. For every AA in H, there exists the inverse of A in G, such that A inverse in H and AA equals the identity. So we're back to the Hermitian thing, right? Which is like a huge thing in group stuff, yeah. Thus, H isn't that beautiful? But then there's a comment here. Maybe you have to recall the definition of a subgroup. No, I did it long form on purpose. If the OP struggled with this question, it shows they don't understand group definitions well enough to take shortcuts. Okay, so that's very good. Yeah, I mean, this is incredibly kind of basic stuff in a way, but
it's an element. Yeah, just because it's an element of that, so it should be a subgroup. If it is an element of a large group, then it should be a subgroup, right? That's the idea.
Yeah, there's a proof there and all, but well, I mean, just this kind of methodology is quite simple, right?
Yeah.
Like whenever you're using group theory, it always seems to come back to this like Hermitian thing.
Inverse, yeah, the inverse has to be in the
group. So a lot of these things are quite simple. I need to like sit down and think about that a bit more. I mean, if this is just the diagonal, they say, and the elementary, I mean, it sounds like they're kind of proving nothing in a way.
Well, inverse has to be in that group.
So what would be the inverse of a diagonal of GG? Is it A inverse? So what is the
kernel? Inverse of the kernel.
Oh, okay. I'm still not entirely sure what a kernel is. It's like the fixed points.
Diagonal thing. Diagonal.
Oh, this is another word for the diagonal, is it?
Yeah.
So that's not the anti-diagonal then, is it?
Well, I'm not sure. Only if it's Hermitian. Something like that is there. If it's Hermitian, then yeah, it will be anti. There's a lot of conditions, you know.
Yeah, that's true. That's
so
true.
It's a very.
Now, where's this isospin? I think I was looking for that. I was looking for a table with some spins in it, but it's not in there. Conformal anomaly is a different thing. So that's good. So I think also U1A was anomalous. Maybe the A stands for anomalous, or as opposed to anti. What do you think?
So we didn't get the answer for A. What is sub SUV and SUA something? We haven't got the answer yet. What they
are. Yeah, that's true, because you were looking at it on the other page, was it? This one, SUL. But actually, because N can be any number, can't it? So it could be 3, right?
Yeah.
So in a way, because I was reading this wrong. I was thinking I was just putting 2 in here.
Can be 3, yeah. It's a
Can be 3, right? So I think we did get our answer slightly, didn't we? Because it's to do with the chiral symmetry breaking that allows for mass to occur. So therefore, mass cannot exist under this, above this value. Like certain types of mass, right? Like baryonic mass. So does that mean the baryons didn't come into existence until after the temperature of the universe fell beneath this value?
Oh, they're called after the when the cold forms.
Yeah, and then there was
when it cools down, cool down period.
Okay, well, let's put this in baryon. Is it epoch or something?
Yeah, epoch.
Baryon. So I think chronology of the universe. So I think we did. Well, we haven't fully understood everything. I think we did get something out of that.
Yeah.
Reionization. I think we want like we need to go back fairly early on for that. Find. Boson. I want to find. Right, it's not found in there. So they're not talking about that. Baryon 250 MeV. But that's for a part. This is CERN. That they have. There's no point in looking at CERN for that. I don't think. They have energy scales at every possible scale, so it doesn't matter. Okay, so I think we'll leave it at that today. Okay. So that was quite long. Yeah, it's nearly 4 hours.
Yeah, thanks. So we will continue probably next week. Maybe we'll see.
Oh, look at that. We can put comments up on the video by just clicking on them. So there's a few more comments here. So JChick2020, I hope I'm saying your name right. He's saying that he self-studied, which is good. That's what we are doing as well. Well, actually, Rajan, you did various physics courses, didn't you? I don't see. I don't have your terms, but as sounds like he's got some theory about black holes and stacking of particles, which is interesting. Same as macro scale. Any different approach? Okay, cool. Yeah, I hear you. There's a lot of people working on their own different projects.
Oh yeah.
Yeah, for sure. Can be quite isolating. So it's why it's good to have communities come together. We've got different guys who come online sometimes. Christian and Manuel, of course, and Gerd. Haven't seen it too much of recently, but
okay. Emmanuel and the other person,
yeah.
Valamontas or somebody, they have put together something. You saw that, RG?
No, I didn't see it.
Yeah, they have put together because Valamontas is talking about. He's using Emmanuel's thing. He's advancing it.
Oh yeah. Okay. Oh yeah. He's doing. Is he the guy working with the dodecahedron stuff?
Yeah, yeah.
Which is funny because that's very close to my work, actually. Well, I mean, just dodecahedrons being related to the 120 cell, but you know, not a million miles away. I think he's in the right ballpark. But if Manuel and himself want to be correct, they need to work with my theory.
Oh yeah.
Do you ever get that, like, where you're just like positive your theory is correct at this point? Yeah, probably isn't. Yeah, it's funny, and everyone's like that as well. You know, loop quantum gravity is correct, and string theory is correct.
I mean, I think, yeah, I will probably M theory after Bell's thing, because I was thinking about M theory for the next episode. But I think the next episode will be, I don't know whether you want to see that. I have the PowerPoint mostly done, but that will be about Bell's theory. If you want to look at that and quickly see whether that's
okay. Well, we do that offline then.
Just a preview of that. I can preview that a little bit.
Okay, you want to preview it? That's fine. Yeah.
So let me. So we go here.
Gravity, space, time.
This is a view of the next episode.
It's a Dr. Dre lyric, isn't it?
Yeah. So let me try to get game. Uh, each time I have to do this. Okay.
Nice one.
So yeah. So gravity and space.
Yeah, I like the
Now,
titles. The title
yeah,
pages are good.
yeah. So called locality. So talks about the mostly Bell's theorem, non-locality. Local hidden variables can't explain entangled states. So Bell's non-locality theorem detached from quantum mechanics, but then he introduced local casualities, and then he had himself gone through a lot of changes, 60s to 80s. I think it's kind of important. And then some align aspect, he tried to prove something about the entangled states. Uh, and then he kind of, in a way, proved Bell's theorem, but uh, let's see. So the Bell's theorem essentially consistency between violation factor special theory was unresolved by Bell, and then fully understood by considering fully Lorentz covariant version of the quantum theory. The Everett interpretation provides the Lorentz covariant quantum theory without action as a distance. So the Everett also comes into picture here, and I mean, I'm just presenting the way it is. I think we have to resolve. There are still a lot of conflicts. So classical physics in locality, yeah, that's so the classical physics says is local. Gravitational and electromagnetic forces propagate to space in finite spaces. Quantum field is principle of locality at field level. Interaction mediated with fields propagate finite speeds. So theory of quantum gravity comes into picture. Loop quantum gravity string theory. Then holographic principle add as CFT. That's now the main thing. Add Andy de Sitter space and conformal field. So Andy de Sitter is like you are sitting inside a box, right? And
No,
seeing
I
what's
think an
happening.
anti-de Sitter space is like is like a cylinder.
Yeah, you are sitting inside a cylinder. Inside a cylinder, what's
Right, and
happening?
the surface of the cylinder
Conformal field theory.
is special relativity, isn't it?
Yeah,
And the interior is general relativity.
yeah.
But it's an inverted form of general relativity.
Yeah.
So it's not actually an accurate picture. But I can improve. I've improved upon that model. I think I've shown that
Oh.
in previous slideshows, but I haven't done any maths with it because I don't actually believe that de Sitter space or anti-de Sitter space or any of that, or the holographic principle for that matter, is right.
Mm.
You know, because like if you look at my research, the AUM model or
Ah.
hypothesis,
Mm.
own, that is basically what they're talking about, but it's a much better model than their version, right?
Mm. How about conformal field theory?
Right, but isn't you see, so that's what I'm confused about. I understand ADS, the anti-de Sitter space, and is it and or conformal field theory, or is like conformal field theory attached to it? Is that where we're talking about if you take a projection of like, let's say, some sort of particle or mass moving in a Einstein, like a so-called Einstein, or like a field, gravitational field, general relativity, and then you project it onto the surface of the cylinder. Is that the conformal? Well, conformal means that when you have
Boundary.
a
It's
circle,
on the boundary. It's on the boundary of the things.
oh, right. So conformal field theory. Yeah. So it's just basically what I just said then, isn't it? what I was talking about. It's a projection of the path of the particle in the field onto the surface creates the special relativity. So it's like, but all of that is fine, but it's not that useful, or like it's not going to like prove anything really, is it? I mean, it's just a nifty little.
So the conformal theory, if the conformal theory is correct, conformal field theory, then whatever is happening in the black hole, if we look at the event horizon, we should be able to get everything, information about the black hole.
Okay. So that's why it's not inverted then, because the boundary is where the black hole is.
Yeah, but the information of the black hole is available, the boundary. What's happening inside, information of whatever is happening inside, it's available on the boundary, kind of thing.
But it's inside the black hole because the boundary is the black hole, isn't it? Or it's at least the event horizon of the black hole, isn't it?
Yeah, exactly.
Okay, so that means that the anti-de Sitter space then is not inverted. I was getting mixed up.
I think it's a perspective. Are you looking outside from inside, or are you looking inside from outside?
Well, it depends where you are. Are you at the center of the cylinder, like the axis, or are you on the boundary, looking in?
Yeah.
Or just outside the boundary? But like,
I would say anti-de Sitter is well inside. Anti-de Sitter will be well inside the cylinder or whatever, and the de Sitter will be well outside the cylinder, but conformally somewhere in between.
Well, yeah, I don't know. Oh, right, I see what you're saying. But isn't de Sitter space like some sort of weird open solution to Einstein's?
Yeah.
Or like application of Einstein's stuff to like general relativity to the Big Bang model to show how the universe expands and eventually cools into this state where all energy is just it's an entropic system where everything just becomes at a ground state or something, and that will happen in the
future.
Like
inside out, right? It's like inside out. You are,
I think that's what they did with anti-de Sitter space. They have, if you're at the center of the cylinder, that's flat space. But as you go closer to the edges, then you would get to like a hyperbolic kind of infinite sort of thing, and then so that would have to be the boundary of the black hole then. Okay, so let's say that's true. So what are you saying from that then, that we can recover information from the horizon? How would we do that?
So whatever is available inside, it's available on the boundary. I think like Susskind, that everybody tried to prove that. I think that and somebody else who got the Nobel Prize also tried to prove that the information is lost. Information paradox. Information is not lost in the the black hole. You can get the information outside the black hole.
Yeah, I don't know about that because, well, if we're going to invert the anti-de Sitter space and not into a de Sitter space, because they're, as far as I know, they're two different things. But
yeah, they are different.
Okay, but if we were to invert it so that the boundary of the cylinder is now on the inside, and the inside of the cylinder is now on the boundary.
It may not be quite that simple because we are not inverting. We are only inverting. The boundary remains the same. We are just inverting so that whatever is inside goes to the boundary. Just go to the boundary.
Just let me finish my point though, because it might be slightly different to what you're thinking. If we were to do this, I'm saying, we were to take the boundary and put it in the center, and take the center and put it at the boundary, like actually invert anti-de Sitter space. And then what would happen is the boundary would be a zero size element, like it would just be a line element going through space-time, and it would be of zero size. And so from the outside, or from the actual boundary now, looking in, what we'd be looking at would have zero size dimension, which is correct according to general relativity. anything that's on the boundary of, or on the, at the event horizon, right, of a black
Mm.
hole should have zero length and also infinite time dilation, isn't it?
Mm.
But then, is that at the event horizon, or is it at the singularity? It doesn't it depend on the size of the black hole, or does it? Well, no, because you'd be traveling at the speed of light once you hit the event horizon.
Boundary. Yeah.
And if you're traveling at the speed of light in relativity, then you will be fully length contracted and time will completely stop. So
Mhm.
so that's correct. So your event horizon should be zero. No, because the event horizon doesn't necessarily need to be zero, does it? Because it's not.
Mm.
It's going to be dependent on the size of the object that collapsed in the first place. The time on the event horizon should be completely stopped. So I don't see how you're going to recover. If you're talking, well, if you're talking about the path of a, let's say, spaceship going around
Mm.
like a sun or a black hole, if you like, whichever, it's in orbit around one or the other, and then you project that onto the surface of either object, which is the boundary. Now we're going back to the normal version. Then you'll get relativity off of that, maybe. But if you're saying that that object is already inside the black hole and you're projecting out, then I don't think that makes any sense, because there's going to be the time for the object has now stopped. So the idea of it moving anywhere, well, I suppose it is still moving, but it's only going to be moving in one direction, which is towards the singularity. So there won't be your projection will just have the dot will just appear not to move, which is the same as time standing still, I guess. I don't know. That's not my area, and I don't really. I think they're wrong anyway. Because I think my model's better, isn't it? It's just better.
Yeah, I think so. Yeah, it's probably advanced. You are advancing for that.
Yeah.
Then
well, I would take them on anytime they want to have a debate. I will absolutely destroy them. Even though they're like, what are they? They are incredibly. Those two guys are very knowledgeable, aren't they? Jared de Hooft and the other guy.
Oh yeah, Hooft got Nobel Prize, right?
Ah, yeah. Like, I mean, they would on any like actual information. Like, if they were to do like some sort of math Olympiad against those two in the specific areas that they're really good at, like general relativity and all, I wouldn't stand a chance. But I just think overall my model is better than theirs and explains more. And that's what I mean when I say I would destroy them.
Who is the other person? Hooft?
Susskind.
Oh yeah, Susskind.
Yeah. I
have listened to many of Susskind's. I learned initially a lot of things from him and Randall, a lot of the general relativity things. I mean, his courses are good, but it diverges, diverges into something. So that I stopped.
You don't feel like he's taking you on a path to like.
No, some of them are good. Some of them concentrate. They are good. And then I had some MIT thing. Then I looked at MIT thing, that also is good, but they start kind of diverging into something else, and that I stopped there because I don't know where they're taking, because I mean,
I didn't get very far with his lectures, though. I have to be honest. I only got
a few of them. I understood few of them, but I stopped there because that I think I understood as much as anybody. If I'm sitting in that course, I probably will pass, understanding. But as good as anybody there, that specific part, I think I can explain as much as anybody. But if you go beyond that, go into more the mathematical things, I don't think I will not. I didn't go into that, into the tensor, the mathematical operations. But I think I have also doubt about that, because I watch one of the guys who is excellent. The Christopher symbol, Christopher symbol thing
Yeah.
is a very important thing because simplifies, and that's what gets into a theory of everything and everything.
But
So there's a upper indices, lower indices, upper indices, how you change them,
the
the
Levi
lower ind
connection.
yeah, the connection, and then just use that manipulation to get to the, the covariant and the variant tensors and connect them into the Dirac things and everything.
Why not
Connect
just
them.
use like a basic polar transformation equation?
Yeah. So I think I have simplified.
Yeah. Well, why not?
I
Like,
yeah, I think my thing goes much further. I mean, they got stuck at some point, but I think
yeah.
I went further because I used similar applied, thing
Well, what did you
of the.
use?
I used that Helmholtz decomposition things like that.
Oh, that
So
sounds. It doesn't. I don't see how that would do what you wanted to do, but and
yeah,
also I think that's quite. That seems complicated enough in its own right, but
yeah, but I can explain the whole thing simple to complex thing. I don't think
yeah.
they can. They
Okay,
can.
fair enough. I mean, I can see it sounds interesting. It's a little bit abstract, but
Yeah.
oh, actually, remember the simulations you were showing
Yeah.
before?
It is very successful. Did I tell you that Emery was very satisfied? He said I did both, and then I don't know whether I showed you that we got excellent result. He's going to publish that.
Oh, good. No, I didn't see that, but he was
I
happy
can.
with the diagrams you made, was he?
Yeah, because see he wanted a simplified math, and I did simplify the math
Oh,
because I said it is sine of theta plus a phase angle. The phase angle is directly related to fine structure constant. It's the inverse of the fine structure constant. So we have very fundamental thing coming
oh,
up. And that shifts. You remember the case one, case two, where the magnetic things happen, and the other one is electric field, the splitting of the, of
yes,
the sinusoidal thing. One is in the magnetic range, one is the electric field, and this is connected with fine structure constant. And I did thank you for the program because I manipulate the program that I could generate. If I can show
right.
you that,
Well, that's good.
I think I probably shouldn't. I don't know. Anyway,
It's up to you, but we can look at that later. But
later, yeah. So perfectly, it's beautiful. So one of the, if I say the phase angle is 0, I get a split in the the photon field. You know, uh, the wave, the
yeah,
half wave. It
you would
splits
have
in the
to.
half wave.
Yeah, you'd have to show me that though.
Yeah, yeah,
I don't
yeah.
understand.
It's very beautiful. I mean, it's a very simple. And the phase is that one hour alpha. I get a split in the thing, and of course I had to use a discrete Fourier. That's why I had to keep working for a long time. But I finally figured out and
Wow.
and
Okay, well, you
and,
have to
and
show me that
simplify the program,
another
simplify
time.
the
When is
Python.
the paper? You show it to us after the paper is published or something like that.
Yeah, yeah, yeah. The Python is it's not that long, like half a page or one page.
Mm.
Does it beautifully. Wonderful
So
result.
I don't know if you want to read some of the comments here on the. Do you want to read some of the comments?
Okay, so let me.
You just go back to the normal way. Oh no, you're not sharing your screen, are you?
Yeah, I have to.
You hit hide. Yeah. Oh no, it didn't work because you're still in full screen. That's why.
Oh, if we hide, okay, I have to get off.
Yeah. You go back to. Yeah.
So this is. You said black hole is the negative charge of the positive white radiation of thermal emission. Wow,
What
is
do you
that the
think?
one?
Yeah.
That's heavy, I think. Are there proof for that? Do they have proof?
No, I think this is his. These are his ideas.
Yeah, I mean it's a heavy thing that's saying, but it should be proved. It's a hypothesis or conjecture.
Yes. Yeah. Exactly. It's his hypothesis.
So
I
you have to
believe
prove.
so.
There should be a proof for that. I think there should be beautiful proof for that. If it
Yeah.
is there, it's a wonderful thing.
Sounds.
Black hole is accumulation of matter. many black holes, micro and macro, but each black hole contains opposite force, particle emission radiation. Not trying to go against anyone, I just want for the advancement benefits of, and just relaying for your math if you agree. Huh.
So yeah, I mean, black hole is a negative charge to the positive white radiation of thermal emission. I'm not entirely sure I understand what that is
Yeah,
because it can be
that's a very heavy
hole,
statement. Heavy statement. You have to break it into what he exactly means.
Oh, okay, okay. But yeah,
I kind of understand. I kind of, you know, I kind of understand that. If I don't know
seems to
whether
me
I'll be interpreted.
connected to what he's saying further down. But each black hole contains its opposite force. So
Yeah,
negative charge and then the positive white radiation. So is it the idea that like a black hole opens out into a white hole?
yeah. It seems like
Uh,
so. He's implying a wormhole. So it means there is a wormhole.
or
That
else
that's
it could be, well, you know the way there's Hawking radiation, but that's not,
that's not what he means. I don't think that.
I don't think so because there's not enough of that, is there, for it to
Yeah,
be opposite?
yeah.
Unless he means opposite, not in magnitude, but just in direction or something. But I don't. Yeah, I don't know. So he's got toroidal sphere. I mean, isn't a toroid a torus?
Four dimensional, right? It's 4D, right? 4D space.
Yeah, I've obviously been. No, I thought is a toroidal not meaning like a torus? Maybe
It goes inside out, right? You go inside, you can come out.
No,
so
not
there's no.
necessarily. I think toroidal is to do with a torus, like a donut shape.
Yeah, so you can go inside and come out the other side without.
Oh, if you mean, and if it's like a wormhole, like a black hole, space time.
No, the torus itself, you go from one side, you keep pathing, and it's a continuous thing. You can come out.
Oh yeah, I see what you mean. From the
Topologically,
like a lattice, yeah, topology, yeah, true. But is that what he means? But what's a toroidal sphere, though? Oh, just yeah, not sure. Okay, so that was good, Rajan. I think we reached the. We got a lot done. We'll have to go back over what we looked at on Wikipedia there another time.
Yeah.
And because I think we got close to something, but we were like,
yeah. I mean, we are skimming on the contemporary physics. I mean, the advanced thing that's going on now. So I think that's good because we are come from 16th century, episode 1, all the way now to episode 7 is almost contemporary, like 1940s, the 19th century. That's what I would say. And then 20th century, which is ongoing, quantum gravity and things like that. And people are still debating about a lot of things. I think we have a better basis because we are looking at the history. So we know what is there, what is not there. We could eliminate a lot of the things, and then that's what I'm trying to do, and that we are trying to do. And then by discussion, we can eliminate those are not possible, and what is possible, then we gather that and look into that more detail, dissect them. And right now, I think we are doing that. For example, the gauge theory, the symmetry and the gauge, loop quantum gravity, and the next level M theory finally, and the brains. So we'll look into that. I think they are going to give, I'm looking little more further into brain theory. I think it's going to give some answers. Even discontinuum physics, I can integrate into that. So I'm trying to do that.
Yeah, it's a bit of fun.
The important thing I am finding is the vector thing and the reference. I think that's where the big thing is going to be, because if you look at the reference, the physics, the logic of the reference, if we solve that, I think we can solve the measurement problem. But it's a little more advanced. I mean, we'll get to it, in a few months.
Yeah. So there was a question I was asking about the general relativity simulations you were talking about previously.
Yeah.
I think there was what I forgot what it was called. You said look up relativity something. Do you remember? Do you know
Oh,
it's like,
numerical relativity.
oh yeah, that's it. Thanks. So I might be able to do something on that
Okay.
next time. I don't
Okay.
know if it's going to be
Yeah,
next
if you
week.
have something, you can present that a little bit.
Yeah, I'm not
Whatever.
sure.
Yeah.
Will it be next week? Because that's coming up to like some sort of holiday break we have. It's like
26. Oh, you have 26. It's like
there's-
Halloween here. Halloween, you have similar thing there, right?
yeah, of course. So Halloween will be around then. I'm not sure if I'm doing something that
End of the
weekend.
month. That's 31st, right?
Yeah, so it'll be middle of the week, but there'll be something going on the weekend, I'm guessing.
26th. So you
Yeah.
we won't have a you won't have a text for 26th.
I don't know, but if we do, it'll be on numerical relativity.
Okay,
So
she'll let
I
us
will,
know.
I'll post that one up, and
Yeah, you can put the link. Yeah, if you have that. Yeah.
okay,
Okay.
yeah. So
Sounds great.
that'll be great. So looking forward to that because
Okay.
I'm doing a kind of a simplified version of certain aspects of general relativity, and I'm sure you can
Okay.
help with that. But
Yeah.
the results I'm getting are like good. Like there was some parts of it that I really wanted to do that seemed a bit difficult, but I managed to get them done, and
Oh,
I
great.
expected them to look a certain way,
Okay.
and they looked that way, and I was like, "Ooh, this is good."
Okay.
And then I had another part which I was like, "Well, this part's easy. I just stick that onto the other part, and then I'll get the right results." But when I run the program, I don't get the results I'm looking for. They're not as good as I'm hoping. So I don't know. There's either some error that I'm doing or something wrong with it that I need to fix. So if hopefully I can fix it in the next week and it should be ready for the weekend.
Oh, great.
Or
Sounds
if
good,
not,
Christopher. So have a nice week, and then we'll see you hopefully next week with
okay,
the numerical relativity thing. Okay. Thanks.
cool. See you later.
Have a
Bye
good.
bye.
You too. Thanks.